Some nights, the stars feel closer, as if the universe itself is whispering its secrets through the silence. You lie there, eyes half closed, and wonder what lies beyond those distant lights. What stories drift quietly between galaxies, unseen, yet eternal. Tonight, we won't rush for answers. Instead, we'll float softly, slowly, through the mysteries that have puzzled humankind for centuries. The kind of mysteries that make you feel both infinitely small and beautifully connected to everything. From the quiet hum of invisible forces to the faraway shimmer of galaxies being born, each holds a secret we can touch only with our imagination. So let's breathe together, in and out. Let the day fade away, and let curiosity become your lullaby. The stars will keep watch, and I'll be here, guiding you through their quiet wonders gently, like the rhythm of your heartbeat in the dark. If this calm space feels like home to you, where science becomes story and sleep comes easily, you can softly tap like or subscribe to drift with me again among the endless mysteries of the night sky. Now, close your eyes and let's begin our journey through the unexplained. Imagine the universe as it once was silent, infinite, and waiting. Then, in a single breath of creation, it began. About 13.8 billion years ago, the universe blossomed from the Big Bang. Not a noise, not a fire, but a pulse of pure expansion. From that moment, space itself began to stretch, like ripples spreading endlessly across a cosmic sea. All that we know, stars, planets, the breath you're taking now arose from that first spark. Yet, what we can see, what we can touch, is only a small sliver of the story. Scientists tell us that all ordinary matter, the stars above, the oceans below, even the thoughts drifting through your mind, make up just 5% of everything that exists. The rest is shadow, dark matter, unseen yet felt, shaping galaxies with invisible hands. And darker still, dark energy, a silent force pushing the universe apart, like an exhale that never ends. When we look into the night sky, we are gazing into billions of light years of vastness, a web of 2 trillion galaxies, each holding its own suns, its own worlds, its own quiet dreams. The same laws of physics guide them all, like gentle notes in a universal song, from the smallest particles humming in quantum rhythm to the grand swirl of galaxies turning through space. And still, there are questions, soft, haunting ones. What is this dark energy that stretches the universe wider each moment? Why does everything move farther away, as if the cosmos itself is drifting to sleep? Someday, scientists say, the galaxies will slip beyond sight, and space will cool into stillness. But for now, we're here floating in the middle of it all, wrapped in mystery, listening to the hum of a universe still expanding. Long ago, before time had meaning, everything that would ever exist, stars, galaxies, even you, was gathered into a single, trembling point, a moment of infinite heat and density, waiting to unfold. Then, in silence deeper than any sound, the universe exhaled. That was the Big Bang, not an explosion in space, but the birth of space itself. From that instant, everything began to move outward, stretching, cooling, and becoming. The echoes of that beginning are still here. If you listen closely, not with your ears, but with the instruments of science, you can hear a faint hum, a whisper of light left behind from the universe's infancy. It's called the cosmic microwave background. a soft glow that fills the sky in every direction. It's the afterimage of creation itself, a memory of when the cosmos was only 380,000 years old, still warm and glowing like embers after a fire. In 1965, two scientists, Arno Penzias and Robert Wilson, stumbled upon this whisper by accident. They heard it not as a sound, but as static, a gentle hiss that refused to fade. What they had discovered was proof that the universe once burned with unimaginable heat, just as the Big Bang had predicted. Long before that, in the 1,920 seconds, Edwin Hubble gazed into the heavens and saw something astonishing. The galaxies were drifting away from us, and the farther they were, the faster they moved. The universe was not fixed. It was expanding, breathing outward. This became known as Hubble's law, a reminder that we are part of an ever-growing cosmos where motion itself is the echo of birth. And in that early expansion, the simplest elements, hydrogen, helium, and lithium, were formed. They are the soft alphabet of matter, the first ingredients from which stars and worlds would one day arise, all of it unfolding in minutes as the young universe cooled and began to take shape. Yet even this elegant story hums with mystery. What came before that first breath? What lies beyond the edge of what we can see? To explain the evenness of the cosmos, its smooth, tranquil vastness, scientists speak of cosmic inflation, a flash of expansion, faster than light itself. It smoothed the wrinkles of space, setting the stage for everything that followed. And now, billions of years later, we drift through that same unfolding, carried by a quiet expansion that began with one breath long ago, in the dark before dawn. After that first spark, the birth of everything, the universe began to stretch, softly, yet endlessly. What once was smaller than a grain of dust started to unfold, like a balloon filling with air, space itself expanding and carrying galaxies along for the ride. In those earliest moments, everything was wild and luminous, a sea of pure energy where light and matter were one, swirling together in brilliant chaos. It was too hot then for anything gentle to exist. Atoms could not hold, only free particles, quarks, electrons, light dancing in a storm of heat and motion. But as the universe breathed outward, it began to cool. Slowly, the storm settled. Quarks joined hands to form protons and neutrons. Then, through the tender rhythm of nucleosynthesis, hydrogen and helium, the simplest elements, were born. They were the universe's first lullaby, the first calm after fire. And behind it all was something even stranger, a moment called cosmic inflation. When the universe expanded faster than light itself, in less than a heartbeat, it grew from the subatomic to the cosmic, smoothing everything into harmony. What once was chaos became balance, the quiet evenness we still see today in the soft glow of the cosmic microwave background, the afterlight of creation. As the expansion slowed and the universe cooled further, gravity began its long, patient work, gathering scattered dust and light, sculpting the first stars, the first galaxies. Inside those newborn stars, heavier elements were forged, glowing and dying in waves of brilliance, scattering the seeds of everything that would come after: planets, oceans, you. The universe did not grow evenly. Like threads in a cosmic web, galaxies gathered in clusters, connected by invisible bridges of gravity. With deep, silent voids between, and even now, billions of years later, that expansion continues, galaxies drifting away from one another, as if space itself is sighing. But there is something mysterious at work in that drift, a quiet force known as dark energy. It's the reason everything is not only expanding, but accelerating apart, a gentle push against gravity, unseen yet everywhere. Its nature remains a secret, hidden even from the light it moves. Perhaps, in that mystery, there's something poetic, the idea that the universe, like us, is still learning how to grow, still unfolding into the unknown, still expanding into silence. Close your eyes for a moment and imagine everything, all that has ever existed, all that ever will, condensed into a single, trembling spark. No space, no time, only potential. Then, in the quiet before existence, the universe took its first breath. In less than the blink of an eye, it began to expand faster than light, faster than thought, swelling from smaller than an atom to something larger than a galaxy. This was cosmic inflation, a moment when space itself unfurled like silk in the dark. Within that first heartbeat of time, the universe set the rhythm that still carries us today. As it expanded, it began to cool. The wild heat softened just enough for the great forces of nature to step apart, gravity first, pulling away from the unified whole, followed by the strong nuclear force, then the delicate twins of electromagnetism and the weak nuclear force. The cosmos was learning to organize itself, to define the rules that would shape everything from the flight of stars to the beating of a heart. And in that same first second, something extraordinary happened. Out of pure energy, quarks began to bind together, forming protons and neutrons, the first stable particles, the seeds of all matter. What had been chaos started to take form, like mist condensing into rain. The young universe glowed with a brilliant plasma, quarks, electrons, and neutrinos swirling together in radiant motion, a sea of light and possibility. As the temperature continued to fall, the first whispers of structure began to emerge. Protons and neutrons clung to one another, forming the earliest atomic nuclei, the beginnings of hydrogen, helium, and the faint promise of everything to come. By the end of that first second, the universe had already written its blueprint, the laws of physics, the balance of matter and energy, the foundations for galaxies, for stars, for life. What followed would take billions of years, but the story was already set in motion, all within a single second of creation. It's humbling, isn't it, to know that everything, your breath, the moonlight, the quiet hum of thought, can trace its roots back to that one heartbeat of eternity, the first second of forever. In the soft afterglow of creation, long before stars were born or galaxies began to swirl, the universe was still a storm, a glowing sea of particles, each too wild and free to settle. Within that fiery ocean danced the tiniest building blocks of all matter, quarks. They were smaller than imagination itself, invisible threads weaving the first tapestry of existence. Quarks are not like anything we can see or touch. They are smaller than atoms, smaller than the protons and neutrons that live in the heart of every atom. They are the essence of matter, the quiet architects behind all that is solid and known. Yet they are also shy, so deeply bound by nature's laws that they can never be found alone. No one has ever seen a single quark drifting freely through space. Instead, they exist only in groups, held together by one of the strongest forces in the cosmos, the strong nuclear force. To understand this force, Imagine an invisible web of energy, a bond so powerful it can overcome the electric repulsion between positively charged particles, binding them together with absolute loyalty. This force is carried by tiny particles called gluons, named for what they do best. Gluons are the glue of creation, the unseen threads that tie quarks together, weaving the first stable forms of matter. In the very first microsecond after the Big Bang, when the universe was only a millionth of a second old, quarks and gluons existed in a wild, glowing sea known as the quark-gluon plasma. The temperatures were unimaginable, trillions of degrees, hotter than the heart of any star, hotter than the fusion fire that would one day light the galaxies. In this primeval plasma, everything moved too fast, too violently, for anything solid to take shape. Matter, as we know it, could not yet exist, but the universe was expanding, stretching outward like a slow breath. And as it expanded, it began to cool. With every fraction of a second, the fiery chaos softened, and the building blocks of existence began to calm. When the temperature finally dropped below a critical threshold, the strong force took hold. Quarks began to reach out, to cling to one another, and in that moment, the first baryons and mesons were born, tiny clusters of quarks bound together. Among them were two very special creations, protons and neutrons. These were the most stable of all baryons, destined to become the heart of every atom that would ever exist. A proton is made of two up quarks and one down quark. It carries a gentle, positive charge, a spark that allows it to connect with electrons and form atoms. A neutron, by contrast, contains two down quarks and one up quark, leaving it perfectly neutral. Together, these two tiny structures, one positive, one still, would become the twin pillars of matter itself. In their formation, the universe crossed an invisible threshold from pure energy into the tangible beginnings of form. It was as if light had learned how to rest, to become something solid. The end of the quark epoch marked a quiet triumph, the universe's first step toward structure. But behind this delicate process was a symphony of deeper powers, the four fundamental forces that govern everything in existence. In those early moments, all four were unified, entwined in a single, elegant force. As the universe cooled, that symmetry began to break. Gravity was the first to drift away, soft, patient, eternal. Though it is the weakest of all forces, gravity has the longest reach. It pulls on everything with mass, shaping the very fabric of space and time. In the far future, it would draw matter together into galaxies, into stars, into the quiet spirals that fill the night sky. Then came the strong nuclear force. Emerging as the architect of matter itself, it bound quarks into protons and neutrons, and later would hold those protons together inside atomic nuclei, overcoming the repulsion between their positive charges. Without it, atoms could never have formed. Without it, the universe would be nothing but drifting light. As cooling continued, the electroweak force, once a single entity, divided in two. From that split came electromagnetism and the weak nuclear force. The weak force is subtle yet vital. It governs the decay of particles and fuels the nuclear reactions that allow stars to shine. It is the hidden pulse that transforms hydrogen into helium in the hearts of stars, releasing light that travels across the universe. Electromagnetism, in turn, became the artist of complexity. It guides the behavior of charged particles, shaping the chemistry of atoms, the electricity in storms, the light that touches your eyes. It is the reason atoms hold together, why molecules form, why life can spark and think and dream. These four forces, gravity, electromagnetism, the strong and the weak, are the cosmic foundation, the invisible laws that compose every note of existence, from the swirl of galaxies to the bond of water molecules. They sing the same eternal song. As the universe continued to expand and cool, the protons and neutrons forged from quarks began to drift closer, forming the first atomic nuclei. This process, called nucleosynthesis, marked the beginning of chemical creation. Within minutes, the first simple elements emerged. Hydrogen, the lightest and most abundant. Helium, its gentle companion. And traces of lithium, fragile and rare. These were the first ingredients of everything, the atoms that would one day ignite into stars, condense into planets, and awaken as life. And as the universe expanded further, it reached another turning point. The hot plasma began to cool enough for electrons to settle into orbit around these newborn nuclei, forming complete atoms. For the first time, the cosmos became transparent. Light could finally travel freely through space. The ancient glow of that moment still surrounds us today as the cosmic microwave background, a faint, warm echo of creation whispering softly across the night. Every beam of starlight, every grain of dust, every living thing traces its ancestry back to that shimmering beginning, to the dance of quarks and gluons, to the moment when energy became matter and silence became song. In the vast stillness of night, it's humbling to remember the atoms in your body, the carbon in your breath, the calcium in your bones, all were forged in that first whisper of creation. You are built from the dust of the earliest stars, from the echoes of quarks bound together in the first second of time. And somewhere, deep within every particle of you, the universe is still humming that same tune, the song of the smallest things. There is a moment in the universe's long night when everything softens. The heat that once roared like a star in every direction ebbs, breath by breath, into something gentler. Particles that could not bear to touch finally slow their frantic motion, and light so long trapped and scattered begins to dream of distance. This is the era of recombination, about 378,000 years after the Big Bang, when the first atoms formed and the cosmos changed its voice from a bright, opaque chorus to a faint, transparent hum. Before this turning, the universe was a glowing plasma, a dense sea of protons, electrons, and photons, colliding and ricocheting so often that nothing could settle. Try to imagine a room filled with sunlight made liquid, where every ray is a crowd, and every crowd is a storm. In such heat, if a proton tried to cradle an electron, a photon would sweep through and pull them apart. Atoms could not yet be, but the universe was expanding. And expansion brings cooling, a long, patient exhale. With each passing moment, collisions lost just a little of their bite. With each degree surrendered, a path opened for quiet to take root. And then, at last, hydrogen arrived, simple, steady, the first to endure. One proton, one electron, a single note held perfectly in the dark. Behind hydrogen came helium, calmer and heavier, with its 2 protons, 2 neutrons, and 2 electrons. No trumpet sounded, no sparks flew, and yet everything changed. With neutral atoms in place, photons no longer scattered at every step, the universe turned transparent. Light could finally travel, not inches, not miles, but across space itself. A flight so long that some of those same photons are still in motion, still reaching us now as the faint, cool glow we call the cosmic microwave background. The coming of atoms is not just a fact in a textbook. It is a shift in the texture of reality. Where there had been only blinding brightness, now there were shadows and depth. Gravity could begin to gather matter more cleanly. Whispers became currents. Currents became streams. Streams became clouds. In those clouds, hydrogen and helium drifted, pooled, and waited. The universe had learned to hold its breath. It had entered a time the poets of science sometimes call the cosmic dark ages, dark not in loneliness, but in potential. A darkness like a field at night before the first fireflies appear. Yet atoms are only the start of a longer, quieter alchemy. In their calm, a new story began, the formation of the first molecules. Chemistry is the language through which matter learns to collaborate, and in the early universe, the first syllables were humble and soft. Hydrogen, with its single electron and gentle charge, was poised to bond. But even in this calmer era, the path to the simplest molecule, molecular hydrogen, H2, was not straightforward. The cosmos had no dust grains yet to catalyze bonds, no complex surfaces for atoms to meet upon. So hydrogen worked with what it had: ionized pathways and patient chance. Two main routes threaded this early chemical tapestry. In one, a hydrogen atom met a spare electron to form the fragile negative ion, H-. Then another hydrogen atom attached, and in the briefest wink, H- shed the extra electron, leaving behind H2. In the other path, a proton and a hydrogen atom bonded into H2-, which then captured another hydrogen atom and released its proton, again forming H2. Neither route is intuitive to a sleepy mind. And that's all right. What matters is the outcome, the universe. In the silence after recombination, began to weave molecular hydrogen out of its simplest threads. Why does H2 matter? Because it gave the universe a way to cool further. Gas that cannot shed heat cannot collapse. It stays puffed up, resisting gravity's slow embrace. But H2, through its subtle vibrations and rotations, can radiate energy away. Like a window opened at night, it lets warmth drift out into space. Clouds that would otherwise hover and sigh began to contract. Under gravity's guidance and H2's soft cooling, the first stars took shape. They were not like the stars we see now. These were the population 3 stars, vast, hot, short-lived furnaces that lit the dark ages with harsh, brilliant light. In their cores, hydrogen fused into helium. Later, helium fused into heavier elements. When those first titans died, they scattered carbon, oxygen, nitrogen, silicon, iron, the ingredients of worlds into the void. Hydrogen had led the way. Helium had steadied the path. In the earliest chemistry, helium formed helium hydride, often called the universe's first molecule, a brief, delicate bond between helium and a proton. H- did not dominate the story for long, but like a single breath at the start of a song, it signaled the beginning of molecular life. Deuterium, a heavy sibling of hydrogen, also entered the conversation, forming HD, which could cool gas even more effectively at very low temperatures. Even lithium, lonely and rare, found fleeting companionship as liage. These were shy presences, scarcely more than hints, and yet together they made the early cosmos a place where chemistry could speak, however softly. Out of this quiet chemistry grew structure. Regions slightly denser than their surroundings, tiny wrinkles imprinted upon the cosmos during inflation, felt gravity's pull just a bit more strongly and deepened into wells. More gas fell in, more H2 formed, More heat leaked away. Protostars awakened, pulled matter into whirling disks, and ignited. Their light poured out in ultraviolet waves that began to reionize the hydrogen around them, ending the Dark Ages in a slow dawn that took hundreds of millions of years. Some light escaped, some was trapped, and in that dance of ionization and recombination, the first galaxies gathered like cities along invisible rivers. Even as these structures took form, the sky carried a relic of the earlier time, a field of ancient light, smooth and nearly uniform, but not perfectly so. Those tiny fluctuations, warm here by a whisper, cool there by a whisper, are the seeds from which everything grew. They are written in the pattern of the cosmic microwave background, discovered in 1965 by Arno Penzias and Robert Wilson, who thought at first they were hearing noise. What they heard was history. The moment the universe turned transparent, measured now with exquisite care by Kobe, WMAP, and Planck, the CMB tells us the universe's age is about 13.8 billion years, that its contents are about 5% ordinary matter, 25% dark matter, and 70% dark energy, that its geometry is astonishingly close to flat. To say the CMB confirms the Big Bang is true, but incomplete. It is more intimate than that. The CMB is the universe's baby picture, light stretched from a warm glow to a cold wash at about 2.7 Kelvin. In its faint anisotropies, its tiny ripples and freckled patterns, we can read the density of matter then, the pull of gravity, the pressure of radiation, the hints of sound waves shivering through the primordial gas. Those ripples, magnified over time by gravity, became the threads of the cosmic web. Along those threads, gas cooled, stars formed, galaxies spun, clusters gathered, and in quiet corners, planets one day circled suns. All of this, atoms, molecules, stars, feels inevitable in hindsight. It was not. Every step required a balance. Expansion versus gravity, heat versus cooling, scattering versus transparency. Recombination made transparency possible. Transparency freed light. Free light cooled the gas in its own way, and H2 cooled it more. Cooling allowed collapse. Collapse lit stars. Stars remade chemistry. In that endless exchange, the universe learned to build complexity from simplicity, and to do so gently, like a tide. Listen closely to the story of hydrogen and helium, and you will hear how modest beginnings become grand symphonies. Hydrogen, the softest note, one proton. One electron became the fuel of stars and the thread of water. Helium, quiet and reserved, shaped stellar lives and the physics of brightness. Stars burn hydrogen to helium. In aging cores, they burn helium into heavier elements. When those stars die, some with a sigh, some with a shuddering supernova, the elements they forged are thrown outward, mixed with gas, cooled again, and bound into new molecules, new clouds, new stars. The cycle turns, and with it the universe deepens its chemistry again and again. As the first atoms took hold, the mean free path of photons, how far they travel before scattering, grew vast. Space itself became a kind of ocean for light, and the CMB is its lingering tide. That ocean tells us more than age and composition. It tells us that the universe's large-scale shape is not curved like a sphere or a saddle, but close to flat, so that parallel lines would neither meet nor drift apart. It tells us that the whisper of inflation, a quick, early swelling, left the sky smooth to a remarkable degree, yet not perfectly smooth, so structure had somewhere to begin. It tells us, perhaps most gently of all, that the laws of physics, those four forces that took their places in the first second, were already guiding the conversation, even in the hush of recombination. There are details that might seem too technical for a lullaby, and yet they are part of the music. The first stars formed more easily in places where HD could cool gas more efficiently than H2 at very low temperatures. The first galaxies gathered where dark matter halos set deep gravitational wells, invisible scaffolds that ordinary matter could fall into. H-Mis flickered in and out of relevance. H-Menas did the quiet work that chemistry required. H2-Mis stitched temporary bridges. If these names blur as you drift, that's fine. What matters is the feeling that chemistry's first steps were delicate and difficult, and that they succeeded anyway. From there, the universe's path is a braid. One strand is gravity, forever gathering. Another is radiation, forever streaming. A third is chemistry, forever finding new ways to bind. And a fourth one, we do not yet understand dark energy, forever urging space to expand a little faster than gravity can hold it back. In the era of recombination, dark energy's influence was quiet, a far-off rumor. Today, it shapes the universe's fate, but the atoms and molecules that began to form then still define the texture of everything. The air in a summer night, the water that remembers mountains, the calcium that keeps time in your bones. When you look at the sky on a clear night, you are seeing the legacy of that first chemistry. The starlight that reaches you grew from hydrogen's fusion through helium's pathways and into heavier elements that paint nebulae and seed worlds. The transparency that makes that view possible was born when electrons let go of light and settled into orbit when space became a window. The faintest hiss of that same transition, the CMB's afterglow, still falls upon us from every direction, as if the universe were a room with a distant lamp, always on, too cool to warm your hands, but bright enough to tell you where you are. If you listen for it, you can almost hear the rhythm. Expansion and cooling, binding and release, collapse and ignition. Over and over, the cosmos follows this breath. In a sense, recombination was the first time the universe learned to rest, not the end of motion, but its refinement. Motion that once shattered atoms now organized them. Heat that once denied form now permitted it. Out of the pause came possibility. To speak of the formation of atoms and molecules is to speak of the moment the universe became capable of memory. Atoms can store light in their lines and levels. Molecules can remember shapes, angles, bonds. Gas clouds can remember cooling. Galaxies can remember the wells they fell into. Stars remember their fuel. Planets remember their birth. And you, made from these same atoms and molecules. Remember too, your body composed of hydrogen, once warmed in a star and carbon forged in a stellar heart. Your breath exchanging molecules that were, not so long ago, the quiet matter between the first galaxies. As you settle into sleep, consider this. The calm you feel in your chest is not so different from the calm the universe found at recombination. Electrons finding their homes, light finding its road, hydrogen and helium, patient and pure, becoming the canvas on which everything else would be painted. From that canvas, the earliest molecules traced the first sketches. From those sketches, gravity drew the first structures. From those structures, stars composed the first verses, and from those verses, worlds learned to sing. The cosmic microwave background still shines, not loudly, but faithfully, 2.7 Kelvin of ancient light. carrying in its freckles a record of small beginnings. The missions that mapped it, Kobe, revealing the first ripples, W-map sharpening the contours, Planck rendering them with exquisite clarity, have given us a near-perfect portrait of infancy. From that portrait, we learned precise numbers, yes, but also a kind of kindness, that the universe did not need to be perfect to become beautiful. It needed only the right kind of imperfections, tiny, balanced, and patient. So, the story of atoms and molecules is not a dry ledger of reactions. It is the tale of how the universe made itself gentle enough to form habits, electrons circling, nuclei holding, clouds cooling. Out of that gentleness came the possibility of seas, of breath, of thought. Out of that gentleness came the space you are in now, the hush, the slow air, the sense that in the dark, something wise is holding you. If your eyes are heavy, let them close. Let hydrogen keep its vigil. Let helium hum its quiet song. The first molecules will watch the door. The background light will keep the hall. Somewhere far, stars are kindling. Somewhere near, your breathing is the metronome of a small, kind cosmos, a universe within a universe, made of the same atoms, following the same laws, resting in the same peace that began when light learned to wander and atoms learned to hold. And as you drift, remember, you are not outside this story. You are its continuation, the living chemistry of a universe that learned to slow down, to bind gently, and to glow. After the first atoms learned to hold, the universe exhaled into quiet. The blinding glow of infancy dimmed, and the sky, once a crowded sea of free electrons and trapped light, became still enough for photons to roam. Yet there were no lamps yet, no stars to paint color on the dark. This is the era we call the Cosmic Dark Ages, a stretch from about 380,000 years after the Big Bang to nearly 1 billion years later, when the first cities of starlight finally rose. Dark did not mean empty. Space was full of neutral hydrogen and helium, of drifting atoms cooling by slow degrees, of dark matter gathering itself into invisible skeletons. Light from the cosmic microwave background sailed through, but to any future eye, there would have been nothing bright to see. No suns, no galaxies, only a soft, pervasive night. In that night, the universe waited like a meadow under snow, quiet but alive with hidden work. The silence was not idle. Tiny wrinkles in density seeded earlier by quantum fluctuations and stretched across the sky by inflation gave gravity a map. Wherever the gas was just slightly denser, gravity leaned a little harder. The neutral hydrogen there felt the tug and drifted inward, like fog collecting in valleys before dawn. Around and beneath these faint condensations, dark matter had already begun to pool, forming halos, deep, unseen wells that ordinary matter would fall into. The cosmos was weaving a scaffold, a web of filaments and nodes that would guide everything to come. Cooling is the secret tempo of structure. Gas cannot collapse if it cannot shed its heat. It stays puffed up, resistant to gravity's pull. In the Dark Ages, without metals or dust, the main coolant was molecular hydrogen, H2, hard 1, in the chemical hush following recombination. Where H2 formed, gas could radiate energy away through subtle rotational and vibrational transitions. Clouds could shrink, densities could rise, slowly, patiently. The first protostellar cores gathered in the centers of dark matter halos, pressing inward under their own weight, until, at last, pressure and temperature kindled fusion. So began the end of the dark. The first stars, population 3, were different from the tempered suns we know. Born from metal-free gas, they were often colossal, perhaps hundreds of times the mass of our sun. Hot and short-lived, their light was fierce, rich in ultraviolet, washing the surrounding hydrogen and stripping electrons away. This is reionization, the slow, uneven lifting of the night as pockets of ionized bubbles expanded around the earliest stars and merged like rising daybreak. These pioneers did more than shine. In their cores, hydrogen fused to helium. Later, helium fused to carbon, oxygen, silicon, and beyond. When these titans died, some collapsing into black holes, others exploding as supernovae, they seeded their neighborhoods with heavy elements. With metals came new ways to cool, new molecules to form, new paths towards smaller, longer-lived stars and the first planetary materials. The universe, once a two-note song of hydrogen and helium, began to learn richer chords. Reionization was not an instant sunrise, but a gradual dawn, unfolding roughly from 150 million to about 1 billion years after the Big Bang. At first, isolated bubbles formed around young star clusters, and later, around quasars, supermassive black holes at the centers of forming galaxies, accreting matter and blazing with accretion light. Over time, these bubbles grew and overlapped, turning a once neutral intergalactic medium back into a thin, ionized mist through which light could travel more freely. The fog lifted, the cosmic night thinned, the grand architecture of galaxies and clusters emerged into view. If you could have watched from within, you'd have seen a choreography, both delicate and immense. In one halo, gas condenses and a star lights. Its radiation carves a cavity in surrounding hydrogen. Winds and supernovae stir the gas, sometimes quenching further collapse, sometimes compressing nearby regions into new star births. In another halo, cooling falters, collapse stalls, the spark is delayed. Across vast filaments, multiple halos gather to form the first proto-galaxies, small, irregular, busy with birth and feedback. These early galaxies would not yet resemble the stately spirals and ellipticals of today. They were clumpy, turbulent, and bright with youth. Underneath this visible drama, dark matter continued its quiet, decisive work. Though it neither emits nor absorbs light, dark matter provides the gravitational backbone of structure formation. Simulations that included simple particles interacting only by gravity produce a cosmic web strikingly like what telescopes infer. Long filaments, dense nodes where clusters form, and wide voids between. Within halos, the rotation curves of galaxies and the motions of stars make sense only if an unseen mass dominates the tally. On the largest scales, the clustering pattern of galaxies and the subtle ripples called baryon acoustic oscillations match a universe where dark matter shapes growth from the start. What dark matter is, we still do not know. It might be WIMPs, weakly interacting massive particles or axions, or something stranger. We infer it from its pull, the way galaxies spin without flying apart, the way light bends around massive clusters, a phenomenon called gravitational lensing, revealing more mass than stars and gas can account for. The way the cosmic microwave background's tiny temperature ripples encode a recipe that demands more gravitating matter than we can see, whatever its nature. During the dark ages it clumped earliest, free from the push of radiation, and summoned ordinary matter to follow. Observing this epoch is an art of listening for echoes. We cannot see the dark ages in visible light. There was very little to see. But we can search for the signature of neutral hydrogen's 21 centimeter line. A whisper in radio wavelengths that tells us whether hydrogen is warm or cool, neutral or ionized, near or far. Arrays on Earth listen for this deep time murmur, teasing out the faint global signal and the fluctuations that track the growth of the first luminous islands. We look, too, at very distant quasars. Their spectra show the Gunn-Peterson trough, an absorption feature that tells us when the intergalactic medium was still mostly neutral, and we read the CMB once more. Not for light itself, but for how free electrons from later reionization slightly scatter it, leaving a faint smear in its polarization, a record of when the first stars turned on. Piece by piece, a picture forms. Around 200 million years after the Big Bang, the first stars flickered to life. By 800 million years, enough galaxies and quasars shone to ionize most of intergalactic space. By about 1 billion years, the dark ages had ended in full, replaced by a young universe of small galaxies, frenzied star formation, and mergers that would, over time, build the grander systems we see nearby. Even now, telescopes that peer into the deep infrared catch the glint of these early structures, their light stretched by expansion, arriving across most of cosmic history to tap our detectors like rain on ancient stone. Within galaxies, a subtler balance took hold between gravity, which gathers, pressure and feedback, which disperse, cooling, which condenses, and radiation, which ionizes. This balance decides whether a galaxy grows gently or burns quickly, whether gas turns into stars efficiently or is blown out to feed the next round elsewhere. The first stars, with their intense output, likely regulated their own neighborhoods severely, lighting the dark, but also thinning the fuel, reshaping the small halos that birthed them. As metals accumulated, cooling pathways multiplied, and star formation settled into more familiar rhythms. What began as the Dark Ages thus becomes the Age of Structure. Filaments feeding galaxies, galaxies feeding stars, stars feeding chemistry, chemistry feeding worlds. The cosmic web is not merely a map of matter, it is a map of possibility. Where the web narrows, galaxies dwindle. Where it knots, clusters blaze with thousands of members. Each galaxy, a city of suns, each sun a chance for planets, each planet a chance for oceans, atmospheres, and dreams. There is a tenderness to this history that can be easy to miss in the sweep of numbers. The universe stayed dark a long time because patience was required. Gas had to cool, molecules had to form, halos had to deepen. The first stars had to live and die to enrich the night. Only then could the softer, steadier stars arise, the kind that live billions of years, the kind that give time enough for complexity to awaken. The silence was not a failure. It was a prelude. If you step outside on a moonless night and let your eyes adjust, the milky spill you see is the matured descendant of that first structure. A spiral disk laid along a filament, spun and stirred by dark matter's hands, lit by countless children of hydrogen. The light reaching you left its stars anywhere from tens to thousands of years ago. The pattern that arranged those stars was set in motion more than 13 billion years before. You are looking not only at beauty, but at memory, the record of a universe that learned to gather itself and shine. And as you breathe, slowly, the way the early gas once cooled, imagine the long night, when nothing visible moved, and yet everything changed. Imagine gravity's quiet insistence, chemistry's first shy bonds, dark matter's steady, unseen pull. Imagine the moment when the first star opened its eyes and the hydrogen around it lifted into light. That is how the Dark Ages ended. Not with a single blaze, but with many small dawns, expanding, merging, and brightening the sky until the universe was threaded with lamps. We live in the glow of those dawns. Every galaxy is a lantern hung on the web they help to weave. Every element, heavier than helium, is a gift from the stars that pierced the dark. And somewhere within you, as carbon breath meets oxygen's embrace, the story continues, the gentle fusion of past into present, of silence into song, of night into the patient, everlasting morning, of a universe that taught itself how to shine. In the long stillness after the Dark Ages, the universe had grown restless again. Invisible threads of dark matter stretched across space, guiding rivers of gas along their filaments. Within those quiet flows of hydrogen and helium, gravity began to whisper once more slowly, persistently, urging the gas to gather, to fold, to fall. Out of that soft insistence came the next miracle, the birth of stars, the first true lamps of the cosmos. Stars are born in molecular clouds, vast, cold swaths of gas and dust, so large that a single one can cradle thousands of future suns. Inside them, darkness is thick, and the temperature can fall below -250 degrees Celsius. It is in that quiet, frigid space that creation begins. Most of the gas is hydrogen, sprinkled with helium and trace specks of heavier dust, remnants of earlier supernovae that enriched the cosmos. For eons, these clouds drift, shapeless and calm, until something stirs them awake. Perhaps a shock wave from a dying star, or the collision of two gas streams, or simply the deep pull of gravity itself. When part of the cloud grows dense enough, gravity begins to overpower the internal pressure that keeps it afloat. The gas starts to collapse inward, slow at first, then faster, drawn by its own growing weight. Deep within the collapse, the center becomes hot and bright with potential. The surrounding material spirals inward, feeding this glowing heart. In time, a protostar emerges, an embryonic star cocooned in the same cloud that birthed it, hidden by veils of gas and dust. The protostar's story is one of rising tension. As more matter falls in, the core grows hotter, squeezing tighter with each breath of gravity. The energy of collapse radiates outward in faint infrared light. But still, the interior temperature climbs. Millions of years pass long enough for entire species of galaxies to drift, and finally, the heart of the protostar reaches about 10 million degrees Celsius. At that temperature, something extraordinary ignites. Nuclear fusion. Hydrogen nuclei protons begin fusing into helium, releasing torrents of energy. In an instant, the protostar becomes a star. The fusion's outflow pushes outward just enough to balance gravity's inward crush, creating a perfect, delicate equilibrium. This is the heartbeat of the cosmos, a balance so steady it can endure for billions of years. Every star you've ever seen, every glimmer in the night sky, is a living example of that equilibrium. The mass of the newborn star decides its destiny. A small, light star, one like our sun or smaller, burns gently, living long, stable lives. Massive stars, by contrast, blaze with intensity, devouring their fuel quickly and dying young. Sometimes after only a few million years, the largest may shine 1,000,000 times brighter than the sun, but their brilliance is fleeting. a candle burning at both ends. Stars seldom form alone. In the womb of a single molecular cloud, gravity works in many places at once, creating clusters of stars born together like siblings. These stellar nurseries, the Orion Nebula, the pillars of creation, and countless others glow softly in hydrogen light, the result of newborn stars illuminating the gas that still surrounds them. Within these nurseries, stars dance together for a while, sometimes remaining bound in open clusters, sometimes drifting apart as gravity's pull relaxes with time. Once a star reaches its balance, when fusion has begun, and the outward pressure matches gravity, it enters the longest, most peaceful part of its life, the main sequence. During this phase, hydrogen in the core steadily fuses into helium. For stars like the Sun, this period lasts around 10 billion years. It is a time of quiet burning, where energy flows outward and light spills into the universe. The balance is perfect, and the star's light remains constant, like a slow, eternal breath. But even stars cannot burn forever. When the hydrogen in the core is exhausted, fusion falters. Gravity, unopposed, begins to squeeze again. The core contracts, and the outer layers expand and cool. The star swells, its color shifting from yellow-white to deep red. This is the red giant phase, a time of transformation and beauty. The Sun, someday, will grow to engulf Mercury and Venus, perhaps even brushing Earth's orbit, glowing thousands of times brighter but far cooler to the eye. In the heart of the red giant, a new kind of fusion awakens. Helium nuclei begin to fuse into carbon and oxygen, forming the first, heavier elements that will one day build planets and living beings. But this phase is brief. For smaller stars, once the helium runs out, no further fusion can sustain the balance. The outer layers drift away into space, forming glowing shells of gas called planetary nebulae, while the remaining core collapses into a white dwarf, a dense ember the size of Earth. But with the mass of a star, it will glow quietly for billions of years before cooling into darkness. Larger stars, however, face a more violent fate. In the furnaces of their immense cores, fusion climbs a ladder of elements: helium to carbon, carbon to oxygen, oxygen to silicon, silicon to iron. But iron marks a wall. Unlike lighter elements, iron's fusion consumes energy rather than releasing it. When a star's core becomes iron, its fire can no longer resist gravity. In a heartbeat, the core collapses. Temperatures soar to billions of degrees. The outer layers rebound. A supernova explosion tears the star apart. For a brief moment, days or weeks, a single dying star can outshine an entire galaxy. The energy of that explosion forges the universe's heaviest elements: gold, uranium, platinum, and more. Everything heavier than iron is born in these cosmic deaths. The explosion hurls this new material outward, enriching the interstellar medium. Over time, the dust and gas from such supernovae gather into new clouds, birthing new stars, new planets, and eventually, new life. What remains after a supernova depends on the star's size. If it was moderately massive, its core compresses into a neutron star, a sphere barely 20 kilometers across, yet more massive than the Sunday. In such a star, gravity has crushed atoms themselves, forcing protons and electrons into neutrons. A teaspoon of neutron star matter would weigh billions of tons. If the star was even larger, collapse continues without end, forming a black hole, a region of space-time so dense that nothing, not even light, can escape its gravity. The universe is, in many ways, a grand story of recycling. The ashes of dead stars become the soil of new ones. The gas expelled from planetary nebulae enriches the next generation with carbon and oxygen, the elements that form life's backbone. The shockwaves from supernovae compress nearby gas clouds, triggering new rounds of star formation. Each generation of stars writes another verse in the cosmic hymn: hydrogen to helium, helium to carbon, carbon to dust, dust to life. This process, stellar nucleosynthesis, is the cosmic alchemy that bridges simplicity and complexity. It begins with the most basic element, hydrogen, and ends with the intricate periodic table of existence. Inside stars, temperatures reach tens or hundreds of millions of degrees, and atomic nuclei fuse in a cascade of transformations. Carbon forms from the fusion of 3 helium nuclei in what is poetically called the triple alpha process. Oxygen follows, then silicon, then iron, the final act before collapse. Fusion is both creation and destruction, a steady dance between pressure and release, between balance and surrender. In every star, this balance defines its rhythm, its brightness, and its fate. And every heartbeat of fusion sends light across the universe. Light that travels for billions of years, light that, one evening, lands softly on your face as you look up. When we say that we are made of stardust, it is not a metaphor, it is literal truth. The iron in your blood, the calcium in your bones, the oxygen in your lungs were all forged in stars that lived and died long before the sun was born. You are, in a very real sense, the universe remembering itself in biological form, the cosmos thinking and breathing and wondering where it came from. Even in their deaths, stars are generous. A white dwarf, cooling silently, gives off its warmth for eons, becoming a dim ember against the dark. A neutron star may spin rapidly, emitting pulses of radiation that sweep across space like cosmic lighthouses. A black hole, though it swallows light, shapes galaxies through its gravity, its presence carving space itself. And yet, for all their grandeur, stars are fragile things born of balance, dependent on the smallest adjustments between gravity and fire. Their lives tell us that beauty in the universe is not an accident, but an equilibrium. Chaos and order, contraction and release, light and shadow, birth and death. Every star that burns, burns to make space for something else, to make us. And every light in the night sky is both an echo and a promise that creation never truly ends, it only changes form. So the next time you gaze upward, remember, you are looking back in time. Each glimmer is a memory, a story unfolding billions of years ago, its photons only now arriving to touch your eyes. Some of those stars are already gone, others are being born as you breathe, and the same processes that shaped them, gravity, fusion, collapse, renewal, are still unfolding endlessly in the deep silence of the universe. In that silence, stars continue their eternal work, turning the simple into the profound, the invisible into the radiant, and darkness into the gentle light that cradles us all. Close your eyes and picture the early universe like a quiet sea after a stormlight has learned to travel. Atoms have learned to hold, and in the darkness between, gravity begins to hum a patient melody. Tiny ripples in density, faint fingerprints left by the Big Bang become the score. Note by note, over hundreds of millions of years, that score is played by hydrogen, helium, and an unseen partner, dark matter. From this hushed beginning, galaxies, vast islands of stars, gas, dust, and dark matter rise like archipelagos from a cosmic ocean. The story begins just after recombination, when the universe grew transparent and photons set out on journeys that would last billions of years. Though space was nearly uniform, it was not perfect. Some regions were ever so slightly denser. Gravity, the subtle choreographer, leaned into these places, gathering matter grain by grain. Dark matter, making up most of the mass, fell together first, forming invisible halos and filaments, a skeletal lattice threading the cosmos. Ordinary gas followed, cooling as it sank into these wells, until clouds condensed, stars kindled, and the first proto-galaxies glowed into being. Nothing about this was abrupt. Gas cools slowly. Stars ignite delicately. Feedback from their light and winds pushes back with equal care. Each newborn star pumps energy into its surroundings. Ultraviolet radiation ionizes nearby gas. Stellar winds stir it, and supernovae explode, sending shockwaves that both sculpt and scatter. These feedback processes are not interruptions, but refinements. They keep galaxies from collapsing too quickly, regulate how fast stars are made, and help set the character of each island of light. Too much feedback, and star formation stalls. Too little, and a brief blaze exhausts the fuel. In this give and take, a galaxy finds its voice. Meanwhile, galaxies almost never live alone. They drift along the cosmic web like leaves on converging streams. And when streams meet, so do the leaves. Mergers from gentle embraces to head-on collisions are common, especially in the crowded early universe. When a small galaxy falls into a larger one, fresh gas can fuel a starburst, igniting thousands of suns at once. When two comparably massive galaxies collide, their orderly disks can tangle and relax into a smoother, elliptical shape. Deep in their hearts, gas funneled inward can awaken or grow supermassive black holes whose outflows and jets add yet another voice to the feedback choir, sometimes quenching star formation in the central regions and reshaping the future. From this interplay, gravity pulling, cooling, condensing, feedback breathing in and out, the familiar zoo of galaxies emerges, each type a different cadence in the same cosmic song. Spiral galaxies are the dancers of the night. Flat disks wrapped with swirling arms, their centers crowned by a bulge of older stars. Within the arms, gas is compressed by slow-moving density waves, like ripples passing through a crowd. The compression kindles new stars, which light the arms in blue-white sparks. Dust lanes trace the spiral's curves. Open clusters and glowing nebulae decorate the scene. Spirals are living things, continuously fed by trickles of gas along filaments or by the quiet absorption of small companions. Our Milky Way is one of these barred, star-forming, and still writing its story. Elliptical galaxies, by contrast, are the deep breath after a storm. They range from nearly spherical to elongated ellipsoids, their light smooth, their colors warm with older, redder stars. Gas is scarce. New star formation is muted or long past. Many ellipticals likely formed through major mergers that scrambled disks and flung stars onto random orbits, while powerful feedback from central black holes heated or expelled the remaining gas. Some are titans, giant ellipticals that anchor clusters, gathering smaller galaxies like satellites. Others are dwarfs, faint and diffuse. Irregular galaxies are the wildflowers, unruly, asymmetric, often gas-rich and bursting with new stars. Tides from close encounters, glancing collisions, or internal turbulence can leave them misshapen yet lively, their clumps of star formation shining like scattered campfires. In many irregulars, we glimpse youthful conditions, as if peering back at an earlier stage of galactic growth. Between spirals and ellipticals lies a quiet in-between, lenticular galaxies, S0, S. They wear a disk and a prominent bulge, but lack spiral arms. Their gas depleted or calmed. These may be spirals that have used or lost their fuel, perhaps through gentle ram pressure stripping in a cluster's hot medium, or through slow, prolonged star formation that left little gas behind. In their restraint, we see the environment's soft hand, guiding evolution without a shout. Beneath every galaxy's luminous face lies the dark matter halo, a vast cocoon whose mass sets the tempo for growth. In more massive halos, gas is heated as it falls in, then cools through radiation to settle into a disk. The halo's depth helps keep gas bound against feedback, allowing extended star formation. In lighter halos, a single starburst or a few supernovae can blow gas outward, delaying growth and leaving galaxies puffy and faint. On the grandest scales, halos cluster along filaments and meet at nodes to form clusters of galaxies, where interactions are frequent and the environment, through tides, mergers, and hot intracluster gas, writes bold edits on galactic lives. As galaxies evolve, many develop bars, elongated stellar structures that act like conveyor belts, moving gas inward to feed central star formation, or black holes, and outward to seed new arms. Others acquire thick disks, stellar halos, and globular clusters, fossil records of ancient mergers and bygone bursts. Even quiet galaxies hum with motion. Stars orbit the center, gas clouds shear and collide, spiral patterns drift. The dark halo breathes with the orbits of countless invisible particles. Each component carries memory. Galaxy feedback takes many forms. Young stars bathe nearby gas in ultraviolet light, ionizing and pressurizing it. Supernovae punch hot chimneys that vent energy to larger scales. Accreting black holes launch winds and relativistic jets that inflate cavities in surrounding gas. Paradoxically, this energy born from condensation prevents overcondensation, keeping the galaxy from burning its fuel all at once. Over billions of years, such self-regulation shapes the diversity we see. Blue star-forming disks, red, quiescent ellipticals, transitional kinds, pausing between songs. Collisions, too, are not merely destructive. They are creative. A well-timed encounter can trigger grand tidal tails, draw out starburst knots, or rearrange angular momentum to birth a new disk after the chaos. The Hubble sequence, our broad taxonomy, from ellipticals through lenticulars to spirals and irregulars, is less a ladder of age and more a snapshot of pathways. Some galaxies settle early into quiet. Others keep accreting, merging, and singing. And the tale continues into the present. Gas still streams in along faint filaments. Dwarf galaxies still tumble into larger halos and dissolve, leaving behind streams of stars like chalk marks on a blackboard. The Milky Way itself is mid-dance, drawing in the Sagittarius dwarf and bound for a slow, stately merger with Andromeda billions of years hence. When they meet, their disks will billow and blur. Their cores will spiral together. In the end, a smoother, brighter remnant may take their place, perhaps an elliptical, perhaps something between. Stars will mostly pass by without collision, but their orbits will be rewritten, and new stars will light where gas is compressed. Through all of this, galaxies remain the universe's workshops. Inside their disks and spheroids, nucleosynthesis in stars builds the periodic table, and supernovae seed fresh gas with heavy elements, dust grains, carbon, silicates, Ice grow in cooling envelopes, drift into nebulae, and become the scaffolds on which molecules assemble. From those molecules, clouds condense. From clouds, stars. Around stars, planets. In this way, a galaxy is not merely a collection of lights, but a cycle, turning hydrogen into homes, starlight into seas, gravity into memory. If you stand beneath a truly dark sky, the Milky Way appears as a river, soft, milky, almost alive. That river is a cross-section of our disk, star by star. Yet the pattern that holds it together, the bar in its center, the arms that unwind from it, the halo of dark matter we do not see, is the same pattern writ large across the cosmos. Billions of galaxies, each with its own history of quiet accretion and sudden change, of gentle regulation and violent rebirth, thread the universe in a web that stretches beyond imagination. And while the physics is precise, gravity's equations, cooling curves, feedback efficiencies, the feeling is simple. Gather, kindle, balance, renew. Galaxies gather the raw material, kindle stars, balance creation with restraint, and renew themselves through death and merger. Their light is the soft chorus we see when we look up, a chorus that began with thermal whispers and grew over billions of years into the grand harmony of the night. So let the image linger as you drift. Dark matter's quiet scaffold, gas flowing like breath, stars lighting in waves, and entire cities of light gliding past one another, sometimes brushing sleeves, sometimes embracing, always changing. Galaxies are the universe learning to make structure from silence, beauty from balance, and again, dawn from darkness. Settle into the quiet and picture a river of stars curling through the dark silver, milk soft and ancient. That river is our Milky Way, a barred spiral with arms that drift like slow music around a glowing heart. Its story is not a single moment, but a patient braiding of many moments, collisions and calms, births and deaths, slow rains of gas and sudden storms of light woven together over billions of years. Tonight, we trace that story as gently as fingertips over a familiar map, letting science become a lullaby of place and time. Not long after the Big Bang, when the universe had just learned transparency and light could finally travel, the seeds of galaxies began to take root. Space was nearly smooth, but not perfectly. Tiny irregularities in density, stretched to cosmic scales by inflation, gave gravity a map to follow. In places a breath denser than their surroundings, invisible dark matter sank inward first, pooling into vast, halo-like wells. Ordinary matter, hydrogen and helium, drifted in after, cooling as it fell, condensing into the first starry embers. This is hierarchical assembly, the universe's way of building large things from small ones. Our Milky Way did not appear all at once. It coalesced from many proto-galaxies, each a small city of stars and gas wrapped in its own dark matter shawl. Over time, these small cities tugged one another closer, merging into bigger towns, larger kingdoms, and finally, into the sprawling spiral we call home. Some mergers were gentle, like streams meeting. Others were rough, like surf flinging stars into long arcs and tidal streams that still lace our sky. Astronomers call this memory, held in motion, galactic archaeology. In the outer halo, you can still read pieces of that past, ghostly rivers of stars, the Sagittarius stream winding around us, the pale signatures of long-lost companions, each strand a story of a smaller galaxy, drawn in and unspooled by gravity's hand. In the ages since, more such infalls have come and gone. The Milky Way is not a closed book, it is an ongoing conversation. While the halo kept the long memory of mergers, the disk learned rhythm. Gas settling inside the dark matter halo carried angular momentum, and so rather than collapsing straight inward, it spread into a rotating plane, thin, wide, and faintly glowing where new stars warmed it. Over billions of years, that plane refined itself into two interleaved voices, a thick disk, older and puffier, its stars tinged with the chemistry of early times, and a thin disk, flatter and richer in metals, where star formation continues like steady breath. In this disk, density waves ripple outward, slow-moving patterns that gently squeeze gas as they pass. Where the squeeze is strongest, clouds cool and collapse, igniting newborn stars. That is how spiral arms keep their whorled grace, not because the same stars remain in them, but because star formation lights the arm like lanterns along a moving breeze. Our sun circles between these patterns in a small neighborhood called the Orion Spur, about 27,000 light-years from the center, far enough from the heart to see the city lights, close enough to feel the hum. Threading the middle of the disk is a bar, a bright, elongated congregation of stars that acts like a conveyor belt, ferrying gas inward to feed the center and outward to seed fresh arms. The bar nudges orbits, organizes traffic, and anchors the galaxy's rotating structure. Around the bar, spirals unwind Perseus, Scutum, Sagittarius, names drawn from constellations on our sky. But really, they are patterns in the Milky Way's own breath. At the galaxy's center lies a dense, old bulge, a spherical, crowded district where stars are packed tight and orbits are tangled. Embedded in that tangle, soft as a whisper yet heavy as fate, is Sagittarius A*, the supermassive black hole whose mass is roughly 4 million suns. It does not roar like its more violent cousins in distant quasars. In our era, it dozes, occasionally flickering in X-rays when a cloud strays too close, but its gravity is the quiet metronome of the inner galaxy, shaping the swirl and shepherding the motions near the core. The bulge itself bears mixed origins. Some of its stars are ancient, born in the galaxy's earliest, more chaotic years. Others likely migrated inward under the influence of the bar, building a boxy, peanut-shaped swell that observers discern when they look through the dust with infrared eyes. In this inner realm, star formation waxes and wanes, gas flows along bar lanes, and the past and present braid tightly together. Beyond the luminous disk lies the stellar halo, thin, diffuse, and old, speckled with globular clusters that orbit like lanterns hung in the dark. Many of these clusters are primordial, their stars metal-poor and tightly bound, fossil beads from the Milky Way's youth. Some came with accreted dwarfs, others formed in place. Altogether, they outline the depth of the dark matter halo, the unseen architecture that keeps the galaxy intact even as its stars move with breathtaking speed. Wrapped deeper still, the dark halo extends far beyond the visible disk, cradling the galaxy in a cocoon of gravity. We cannot see it, but we feel it. In the way rotation curves stay flat instead of falling, in how satellites orbit, in the resilience with which the Milky Way holds itself together against the tug of neighbors. Dark matter is the stage the Milky Way dances on, and the stage is vast. Stars tell time by their chemistry. Early generations, born when the universe had only just begun enriching itself, carry few heavy elements. Astronomers call them metal poor. Later stars like the Sun carry the ash of countless supernovae and dying giants. Carbon, oxygen, iron, calcium, all the familiar letters of life. This gradual enrichment chemical evolution is the Milky Way's diary in elemental ink. As stars live and die, they return material to the galaxy, gently through winds, dramatically through supernovae. Those elements dust the clouds, cool the gas, and allow it to fragment more easily, which changes the kinds of stars that form. Early on, without metals to help cool, stars tended to be massive and short-lived. As metals accumulated, the galaxy favored more modest, longer-lived suns. Over time, this slow feedback loop allowed planets to rise from disks of dust, rock, and ice, collecting into worlds. Somewhere on one of those worlds, oceans learned to dream. The Milky Way moves through space with companions. Two of the most luminous are the large and small Magellanic Clouds nearby dwarf galaxies in the southern sky. They trail a Magellanic stream of gas that arcs behind them like a comet's tail, a river likely stripped by gravity and tides. Some of that gas will rain onto the Milky Way, feeding future star formation, a quiet promise of tomorrow's nurseries. Their pull, and the pull of other satellites, has likely warped the Milky Way's disk, giving it a subtle tilt and ripple, as if a pebble had been dropped into a pond of stars. Meanwhile, the Sagittarius dwarf is being cannibalized even now, its stars wound into multiple wraps around our galaxy, a reminder that growth and change are not only ancient habits, but present ones. Across the halo, stellar streams trace the paths of long ago infalls. Each is a thin scar of gravity, a memory you can follow from horizon to horizon if your eyes could gather 10,000 nights of starlight at once. Closer in, the bar at the center rotates slowly, stirring the disk like a spoon in a galaxy-wide cup. Over billions of years, that stirring helps stars migrate, some moving inward, some outward, softly reshaping the patterns of age and metal across the disk. The result is a galaxy that looks calm but is always in motion, like a sleeping ocean whose tides you only notice if you wait long enough. The galactic center is busy. Molecular clouds jostle close to the bar's ends. Young, hot stars blaze where you would least expect them, and magnetic filaments thread the region like harp strings. Near Skr A*, some stars cut tight, fast orbits, year-long loops traced in decades of careful watching, offering direct, elegant proof that a supermassive black hole sits there. Most days, Skr Times is quiet, swallowing drifts of gas without much fanfare. On rare occasions, it flares, like a sleeper turning in bed, lighting the inner parsec for an hour before dozing again. Even in slumber, its gravity shapes the flow of gas and the choreography of stars. Look around from our neighborhood in the Orion Spur, and the Milky Way is busy but measured. Giant molecular clouds collapse into clusters. H2 regions bloom pink where newborn stars ionize hydrogen. Supernova remnants spread their filaments like thistledown, and along the arms, dust lanes draw charcoal strokes between light and light. Above and below the disk, a faint stellar halo flickers with ancient embers, while the far outskirts host the dim reaches of the circumgalactic medium, a thin, hot reservoir of gas that exchanges breath with the disk, catching outflows and feeding inflows in a grand, slow cycle. The Milky Way continues to accrete, trickles of gas along filaments, wisps torn from satellites, a steady infusion that keeps the star-forming engine idling. Sometimes the engine surges, sometimes it rests. In the long average, it hums. If you could listen with radio ears, you would hear the neutral hydrogen of the outer disk whisper in a 21-centimeter line, mapping the spiral from its faintest edges inward, showing warps and waves stirred by passing dwarfs. Galaxies are held between two truths. Gravity gathers and feedback disperses. In the Milky Way, clustering stars and the central black hole both return energy to their surroundings. Winds, radiation, and the occasional jet or bubble discouraging the gas from collapsing too quickly. This self-regulation keeps the galaxy from burning out, letting the disk make stars steadily for billions of years. Environment also matters. In looser suburbs of space, spirals like ours keep their gas and keep their arms. In crowded clusters, galaxies often lose gas to the hot intracluster medium, their star formation fading as they are stripped. Our Milky Way lives in a small town, the local group with Andromeda, M31, as its peer and dozens of dwarfs as its neighbors. Here, tides tug and streams form, but the environment is gentle enough for a spiral to keep dancing. How old is a home? The Milky Way's age is written in its oldest stars, some older than 13 billion years, and in globular clusters whose light has been crossing space almost since the beginning. The oldest halo stars whisper of a time when the galaxy was not yet a disk, only a gathering. The thick disk speaks of an era of more energetic mergers, a period of heating and upheaval that puffed the early plane. The thin disk tells the long, stable tale, since the slow, musical making of spirals, the steady choreography of arms and bar. Even our sun fits into this tapestry. 4.6 billion years old, born from a nebula enriched by countless earlier deaths, orbiting the center every to 230 million years, a single galactic year. We are midway out in the disk, where the night is dark enough to see and bright enough to feel belonging. Our galaxy's satellites, the Magellanic Clouds, Sagittarius, and many fainter dwarfs, are both companions and contributors. They tug on the disk, they offer up gas, they shed stars into streams, and in the long run, many of them merge, adding their mass to ours. Each brings its own chemistry and clusters. Each leaves its trace in the halo and in the motions of stars. If you could peel back the Milky Way's layers like tree rings, you would find these mergers marked in distinct bands, epochs when the galaxy grew a little older, a little larger, a little more complex. The Milky Way's most dramatic future is a rendezvous already scripted by gravity, a collision with Andromeda, our nearest large neighbor, in roughly 4 billion years. From some vantage point then, the sky will blossom with a second spiral rising over the horizon of stars. The two disks will draw near, pass through, and swing back, sparks of star formation kindling along compressed gas lanes. Over a few close embraces, hundreds of millions of years apart, their shapes will morph, arms unspooling into tidal tails, bulges merging, central black holes spiraling inward to finally coalesce in a flash of gravitational waves. Despite the drama, stars rarely collide. Space is mostly space. What changes are orbits. The combined system will likely relax into a more elliptical form, its star formation settling or quenching depending on how much gas remains after the dance. Some stars will be flung into wide, looping paths. Others will sink toward the center. If any beings watch from some future shore, they will see a new galaxy take shape, sometimes nicknamed Milkomeda, quieter, larger, and bright at the core where two black hearts became one. Beyond that merger lies a long twilight. Star formation will ebb as gas is consumed or heated and not returned. Over trillions of years, the bright sketches we know, arms, bars, lanes, will fade. White dwarfs will cool. Neutron stars will spin down. Black holes will keep their counsel. Yet for a very long time, much longer than any human word can hold, there will still be light in some corners, still planets circling quiet embers, still the memory of spiral music in the orbits of old stars. And even as the broader universe expands faster, carrying distant galaxies beyond any future line of sight, the local group will remain gravitationally bound, an island of matter in an ever-widening sea. The Milky Way's descendants will keep company with Andromeda's, and with the remnants of today's dwarfs, in a small archipelago of enduring mass. In all of this assembly and accretion, disks and bars, stars and streams, there is a simple comfort. The Milky Way is not an abstraction, but a home. Its ingredients made the water you drink and the bones you carry. Its cycles gave time for oceans, forests, and stories. When you look up, what you see is the present tense of an ancient, ongoing work. Gravity gathering, fusion kindling, feedback balancing, mergers renewing. If you let your breath slow to match the galaxy's long pulse, you can almost feel the steps, small halos meeting, a disk forming, a bar stirring, arms lighting and dimming, streams winding through the night, companions tugging at the edges, a future spiral rising in the distance. The science is precise, and the feelings it invites are soft. Structure from silence, memory from motion, life from ash. So rest here, in the curve of one arm of a barred spiral, 2/3 of the way out, inside a spur with a sun that hums. The Milky Way took 13+ billion years to make this room for you, this corner where starlight arrives on schedule and gravity holds the floor steady, and it will keep remaking the room long after we sleep. We are not separate from its saga. We are a chapter in its long, turning page. And as you drift, the galaxy turns calm, immense, and tender, carrying us with it, always home. Before there were calendars or oceans or names for the wind, there was a cloud, a hush of gas and dust drifting through a quiet lane of the Milky Way. It was unremarkable by galactic standards, mostly hydrogen and helium, salted with tiny grains of silicates, metals, and ice as ashes from older stars that had lived and died long before. Then, somewhere nearby, a star ended with a shout. Its supernova shockwave rippled across space, pressing into the cloud, and what had been content to drift began to collapse. As the cloud fell inward under its own gravity, it conserved angular momentum and spun faster, spreading into a thin, rotating disk, a luminous plate of dust and gas with a hot knot forming at its center. That knot was a protostar. The plate was the solar nebula, and the faint, glowing seams through it were the first scaffolds of our solar system. Material circled and spiraled inward. Grain stuck together. Pebbles met and grew. In the center, pressure and temperature rose until, at last, hydrogen nuclei fused into helium. Light poured outward, and our sun took its first steady breath. Around this newborn star, creation proceeded by patience. Dust grains bumped and clung. Pebbles turned to boulders, boulders to planetesimals, mountain-sized bodies whose gravity could gather more. In the mild furnace of the inner disk, where sunlight ran strong and temperatures were high, only metals and silicates could condense and endure. Here, the terrestrial planets took root, Mercury tight and iron-rich, Venus shrouded and bright, Earth blue in the making, Mars small and rust quiet, each assembled by accretion, each shaped by collisions that warmed their interiors, each learning the choreography of orbits that would hold for billions of years. Farther out, past an invisible boundary called the frost line, sunlight softened and cold returned. Water, ammonia, and methane could freeze into grains and ices, adding mass quickly. There, cores grew large, fast, big enough to tug on the nebula's lightest gases. Jupiter and Saturn inhaled deep, gathering thick mantles of hydrogen and helium until they became gas giants. Worlds too vast for any simple comparison to grasp. Uranus and Neptune, slower in their growth and farther from the sun's abundance, became ice giants, rich in water, ammonia, and methane ices, their atmospheres tinted in cool blues. Not all the material found a planet to call home. In the cooler's margins and the outer dark, countless ices and rocky fragments settled into reservoirs the Kuiper Belt beyond Neptune, a ring of frozen, small worlds and comets, and farther still, the long, dim halo of the Oort cloud, a deep pantry of icy bodies perturbed from time to time by passing stars. Scattered among these shelves were dwarf planets, Pluto among them quiet archives of the solar system's first drafts. In this story, Jupiter is not just a character, it is a conductor. Its gravity-shaped paths, stirred orbits, and sometimes flung smaller bodies inward or outward. In some models of our system's youth, the giant may have migrated tacking inward and then outward under the push and pull of the disk, tilting the balance of where rocky worlds could grow and where water could ride in on icy messengers. However the details unfold, Jupiter's presence helps sculpt the architecture we now inhabit, the spacing of planets, the leftovers in belts, the pathways comets trace when they fall sunward and blaze. The young solar system was not gentle. For tens of millions of years, growth meant impact. Worlds to be colliding, merging, melting, and cooling again. The Earth gathered quickly, perhaps half its mass, in a geologic blink, then slower still. In that chaos, a giant impact likely struck our forming planet, a Mars-sized body, sometimes called Theia, glancing the young Earth and ejecting debris that ringed the planet and coalesced into the moon. The scars of that violence faded with time, but the consequences endured. The moon has since steadied Earth's axial tilt, gentled our seasons, and pulled on our seas, her tides an ancient metronome for life. Even after the major building ceased, the solar system went through a long aftershock, a spike in impacts, often called the Late Heavy Bombardment, roughly 3.8 to 4.1 billion years ago in some reconstructions. Craters on the moon preserve that memory like pockmarks on old skin. On Earth, plate tectonics, weather, and time have erased much of the record, but hints remain in ancient crystals and rocks. Some of those late arriving comets and asteroids brought water and organic molecules, freshening oceans and possibility. How do we know this story? We read it the way archivists read fragile letters, slowly, from multiple angles. We look into protoplanetary disks around young stars, rings glowing in radio and infrared, catching new systems partway through their making. We run simulations that let gravity and gas dance on fast forward, testing which first steps lead to a system that looks like ours. And we hold meteorites, the oldest rocks we can touch, dating their minerals, measuring their isotopes, and hearing in their composition the inventory of the nebula that built our home. All of this happened not in a vacuum, but in the Milky Way's long embrace. The solar system formed in the Orion Arm, a quieter lane between the galaxy's grander spirals, far from the turbulent radiation and gravitational crush of the galactic center, close enough to the galaxy's reservoirs to be well supplied with metals and dust. The Sun is not the first star to live here, and it will not be the last. Before it, generations of massive stars fused heavy elements and returned them to the interstellar medium through winds and supernovae. That is why our planetary recipe contained iron for a core, silicon for crust, oxygen for water, carbon for life. The galaxy wrote the pantry list, and the solar nebula cooked. Earth's own becoming reads like a fable told in layers. As the planet accreted, impacts and radioactive decay heated it from within. The interior melted enough to differentiate. Heavy iron and nickel sank, forming a core. Above it, a thick mantle of silicate rock, and at the top, a provisional crust. That metal heart began to move. In the outer core, molten iron convected, generating a magnetic field that would, in time, guard the atmosphere from the sun's charged particles and cosmic rays. This invisible shield, the magnetosphere, keeps solar wind from stripping the air, preserves water, and protects the chemistry that life requires. Volcanoes exhaled the planet's first atmosphere: water vapor, carbon dioxide, nitrogen, and traces of methane and ammonia. In the beginning, it was a blanket too warm for clouds to linger. But as Earth cooled, rain fell and fell, pooling into basins, carving paths, and making oceans. Water, with its subtle capacitance for heat and its gift for dissolving, became Earth's grand mediator, softening climates, transporting nutrients, inviting chemistry to tangle itself into more elaborate shapes. On and within the crust, the planet's long breath began. Plate tectonics, driven by mantle convection and the slow loss of planetary heat, Earth's lithospheric plates slid, collided, and rifted, building mountains, opening oceans, and recycling the crust in long cycles measured in tens of millions of years. This restlessness became a climate guardian. Through the carbon silicate cycle, rain and weathering drew CO2 from the air into rocks. Subduction carried those rocks inward. Volcanism returned CO2 back to the sky. Over deep time, this thermostat has helped keep Earth's temperature in the narrow band where liquid water and life can persist. Within this dynamic setting, the improbable began to feel inevitable. In warm pools and deep-sea hydrothermal vents, on mineral surfaces, and within droplets, organic molecules assembled, broke apart. At some point, still debated, still mysterious life took hold. Chemistry learning to copy, to compartmentalize, to use energy and store information. Early life on Earth likely breathed in an atmosphere without free oxygen. That came later, when photosynthetic organisms, ancient microbes, learned to harvest sunlight and split water, releasing O2 as waste. Over hundreds of millions of years, oxygen built up. The Great Oxidation Event transformed the sky and the oceans, rusted the rocks, and opened the door for more complex metabolisms and, eventually, organisms with lungs. The story of life radiating outward entwines with the story of Earth's stability. Our planet orbits in the sun's habitable zone, not too close to boil the oceans, not too far to freeze them solid. The moon stabilizes Earth's tilt, smoothing the extremes of seasons. The magnetosphere deflects charged particles. The ozone layer, born from oxygen high in the sky, filters ultraviolet light that would otherwise shatter DNA. Water cycles among sea, sky, and stone. Nutrients circulate through continents and back. whether kind and harsh, by turns mixes the ingredients of continents and oceans so that no place is static for long. The result is a world where change is the condition of stability, a balancing act that has held for billions of years. Beyond Earth, the solar system bloomed in variety. Mercury kept a great iron core and lost most of its volatiles, a scorched pebble hugging the Sunday. Venus, Earth's sister in size, ran hot with a runaway greenhouse, its clouds opaque and acid soft, its surface a pressure cooker where lead would flow. Mars, smaller and cool, once held rivers and lakes, perhaps shallow seas. Its air thinned, its interior quieted, and the water retreated beneath rock and ice. Farther out, Jupiter's moons became a miniature world system. Io volcanic and feverish, Europa and Ganymede harboring subsurface oceans beneath ice, warmed by tides. Saturn's Titan with thick nitrogen air and methane lakes. Enceladus feathering space with plumes rich in water and organics. The outer giants, Uranus and Neptune, spin with pale storms and hold clues to planetary formation, still being teased from telescopes' data. Between Mars and Jupiter, the asteroid belt preserves fragments of planetary beginnings, some dry and metallic, some carbon-rich and dark. Beyond Neptune, the Kuiper belt holds small, cold worlds with exotic ices. Their surfaces record collisions and cryovolcanic reshaping, and the slow, cosmic weathering of sun and space. All of these places are footnotes and forewords to Earth, reminders that while our planet is an oasis, it is not the only bearer of complexity or surprise. Through billions of years, orbits have shifted slightly. Resonances have played their subtle tunes, and the system has kept time. The outer planets likely migrated in early epochs, exchanging angular momentum with leftover planetesimals, sculpting belts, and scattering comets. Collisions have not ceased. They have only grown rarer and, usually, smaller. Even today, meteoroids graze our atmosphere and light up the night in brief, dissolving strokes. Once in a while, a larger body reminds us that the solar system is a dynamic neighborhood, not a still life. From the Milky Way's point of view, the solar system is a speck, a patient clock circling every 230 million years as the galaxy turns. And yet, in this small, bright room, everything familiar arose. The chemistry of rain, the architecture of cells, the intelligence that can speak these words. None of it required miracles. All of it required time, energy, and the right balance of forces. The sun's steady output, the Earth's size and heat flow, the moon's tug, the protective magnetic field, the slow disciplines of plate tectonics, the persistence of liquid water, the galaxy's long provisioning of elements. Each became a thread, and the tapestry holds because the threads hold together. We know this story, in part, because we can touch it. We pick up meteorites whose minerals froze in place before Earth was fully formed. We read isotope ratios that tell of stellar forges and nebular temperatures. We analyze zircons older than almost any other piece of Earth's crust, their oxygen isotopes, hinting at early oceans. We build models and test them against the sky. We send spacecraft to sniff the breath of comets, to land on asteroids, to sample the soils of Mars, to feel the frost of the outer moons. Each measurement is a candle in a large room. Together, they reveal furniture, walls, a window open on a wider night. Every star, if given a disk and patience, will attempt a version of this story. Some will fail early, Some will build only hot Jupiters. Some will raise super-Earths or ring giants by the dozen. The exoplanet census tells us that planet making is ordinary, a galactic habit. But the particular composition of our solar nursery, the metals available, the distance from the galactic center, the quiet of our Orion arm lane help set the terms of our plot. It is both humbling and comforting to know that we are at once typical in the methods of our making, and particular in the details that formed this pond and these forests, and the breath you are taking now. If you listen to the solar system as you would listen to the sea, you can hear its long rhythm, collapse and spin, accrete and ignite, cool and condense, impact and heal, orbit and endure. You can hear the sun at its center, converting mass to light with patient generosity. You can hear the planets, each fretting out its own melody. You can hear the thin hiss of radiation, the quiet patter of dust, the distant clatter of a comet's periodic return. And in the midst of that, you can hear Earth's softer notes, clouds turning, tides walking, plate boundaries grinding, rain naming stone, a music that, against all odds, learned to sing back. So rest in this small, bright room, in this corner of a spiral arm, where a star's warmth holds oceans in place and iron spins beneath your feet to keep the sky intact. Outside, the Milky Way turns. Outside that, the universe continues its expansion into a silence too vast to measure with feeling. Inside, on a world born from dust and tempered by fire and water, life arranges itself into forests and coral and thought, and then into stories that carry us gently to sleep. The solar system and the Earth within it are the patient result of ordinary laws working for an extraordinary length of time. And somehow, that patience, more than thunder or spectacle, feels like grace. Dark energy enters this story like a breeze you cannot feel on your skin, but watch in the grass, an influence everywhere and nowhere. Quiet, yet decisive, it holds roughly 2/3 of the universe's total budget, a soft pressure woven into the fabric of space itself, and it is the reason distant galaxies drift faster apart the farther away they are. When astronomers measured the fading of far-off supernovae and found them dimmer than they should have been, the result was not a mistake in the candles, but a revelation about the room. Space was not merely expanding, the expansion was accelerating. The implication is simple and strange at once. There is an energy of emptiness, a tendency for the stage to widen of its own accord. Call it a cosmological constant with a value that never changes, or imagine a field whose properties might slowly evolve. Either way, its effect is to tilt the long arc of time towards separation. This acceleration is not a rushing panic. It is a gentle bias that, over billions of years, profoundly reshapes the possibilities for structure. In the youthful universe, gravity led. Small fluctuations grew into halos. Halos fostered stars. Stars enriched gas. Galaxies blossomed. As dark energy comes to dominate, the contest turns. Gravity still sculpts locally within galaxies, within clusters, but on the widest scales, the fabric continues to stretch. Filaments lengthen, voids widen, and the grand web that once grew denser begins to thin at its edges. Left entirely to gravity, the cosmos might have recollapsed. With dark energy, steady and positive, it thins instead, asymptotically cool and slow, a long winter of distance. And if, in some far-off story, the repulsive pressure were to grow stronger than constant, a possibility in some speculative models. Then the widening could become a tearing, a big rip that unthreads even bound systems. That is not tonight's certainty. It is only one more whisper at the edge of what we do not know. Between the small and the all lies the terrain of galaxy evolution, a landscape where gravity gathers and feedback breathes, where chance encounters leave fingerprints in starlight. A galaxy's path depends on its mass, its supply of gas, the quiet or crowded nature of its environment, and on the histories of its neighbors. At first, galaxies were modest, knots of gas cooling in dark matter halos. Their first stars, bright and short-lived. Their chemistry simple. With each generation of stars that lived and died, gas cooled more efficiently, fragmenting into smaller clouds, favoring longer-lived suns and richer populations of elements. Spirals developed, ordered rotation and pattern. Ellipticals, often forged in mergers, settled into smoother light. Inside a spiral, the arms are not fixed structures, but roaming compressions, like traffic waves moving through a disk. As an arm passes, gas is gently squeezed, cooling more quickly, collapsing more readily, and star formation brightens the lane in blue. Over time, the reservoir of cold gas in some spirals begins to wane. Starbirth consumes it. Stellar winds and supernovae heat, and sometimes expel it, and the circumgalactic medium trades inflow and outflow like a slow tide. As gas thins, the galaxy reddens, not from paint, but from aging. Blue, short-lived stars vanish quickly, while old red stars linger. The music quiets, but does not cease. In ellipticals, the tempo is different. Their stars often formed in bursts, starbursts, ignited when disks collided and gas clouds slammed together, condensed and lit. Yet those same violent beginnings left the galaxies with less cool gas for the future. Hot halos and central engines stir and heat what remains. New stars become rare, and the light smooths into a warm, steady glow. In little irregulars and dwarfs, the drama is more sensitive. A few supernovae can rattle the whole system, blowing gas outward, delaying the next round of growth until the wind drops and the gas falls back. Threaded through many galaxies is a deeper furnace, a supermassive black hole at the center, ordinarily quiet, sometimes blazing. When gas spirals inward to feed it, the process can power an active galactic nucleus, AGN, a beacon whose radiation and winds can regulate the whole city. Energy pours out along jets and into bubbles, pressurizing the surrounding gas, preventing it from cooling too quickly, modulating the rate at which the galaxy can make new stars. This seems like an odd kindness from a dark heart, but it is part of the general pattern. Feedback from stars and black holes keeps galaxies from using up their fuel in a single storm. Regulation is not an interruption of growth. It is the reason growth can persist for billions of years. The universe is social. Interactions and mergers shape galaxies as surely as internal processes do. When two galaxies pass, tides pull on their outskirts, drawing out tails and bridges, twisting disks into bars, funneling gas inward. When they merge, their stars mostly pass by one another without collision, but their orbits are rewritten. Their gas is shocked and compressed, and star formation can flare by factors of 10 or 100 for a brief, brilliant time. In the wake, the remnant relaxes, sometimes into a larger disk if there is still gas to settle, sometimes into a rounder galaxy if the collision was a match of equals. Pairs become one. Groups become clusters. Clusters thread the web. These dances are not merely spectacle. They are formative. Many ellipticals bear the signatures of past mergers, shells and ripples in their outskirts, kinematics that tell of stars thrown onto random orbits, central cores puffed by past AGN outflows. Bars and spirals may be the fossils of encounters or the self-organized response of disks to their own gravity. Either way, they are conveyors, sending gas inward to grow central bulges and feed black holes, and outward to seed new arms. Even in isolation, a galaxy is negotiating with its past. Gas cycling between hot halo and cool cloud. Stars migrating radially through the disk under the nudge of spiral patterns. Chemical gradients smoothing as orbits mix. Dark matter, the quiet scaffold, is present in every scene. It sets the depth of the well, the speed of rotation, the resilience against feedback, the likelihood of a galaxy holding on to its gas after a burst. In deep wells, gas that is heated can still remain bound, cooling again later to make more stars. In shallow wells, one large burst can loft much of the gas away, leaving a dwarf to fade. On even larger scales, the cosmic web itself is a river system. Gas streams along filaments into halos, feeding disks over time, while outflows from supernovae and AGN seep back into the halo and sometimes into adjacent filaments. A slow exchange between structure and the medium that surrounds it. As the universe ages, star formation overall declines. The peak came when the cosmos was less than half its current age, a time when gas was abundant and mergers were common. Since then, the average galaxy has been coasting, still forming stars, but more slowly, more quietly. The phrase astronomers sometimes use, quenching, sounds abrupt, like a snuffed candle. But in most systems, it is a soft dimming, driven by gas exhaustion, environmental effects, and central heating. In crowded clusters, galaxies feel the ram pressure of the hot intra-cluster medium. Their gas is stripped, their star formation wanes, and they join the red, quiescent population. In the field, galaxies fade on their own schedule, set by supply and feedback. The thread of collisions continues across the eons, each encounter changing the participants, and on rare occasions, their very category. A spiral can become lenticular after losing its gas, wearing a disk without arms. Two gas-rich spirals can make an elliptical. Two dwarfs can make a larger dwarf. In these events, supermassive black holes do what their host galaxies do. They too merge. In the slow inward spiral of two central black holes, energy goes somewhere. It goes into stars that are hurled into wider orbits, into distortions of space-time itself that propagate outward as gravitational waves, into heat and motion in gas that flows close and is shocked into light. Dark energy writes itself into this narrative, not with a sudden plot twist, but with a gradual edit of the backdrop. Over long times, clusters that are now bound remain so. Groups stay together, but farther structures recede beyond any future line of sight. The playground shrinks to local neighborhoods, while the universe on the whole grows sparsely lit. Within the neighborhoods, evolution persists. Galaxies continue to merge where orbits demand. Stars continue their cycles of birth and death. Central engines flare and rest. Gas continues to trade phases. The global star formation rate might fall, but locally, the story remains busy, intricate, alive. Observationally, we piece this together like listening through walls. We map the cosmic microwave background to learn the initial conditions. We survey galaxies across cosmic time, using their redshifts as a clock. We read color magnitude diagrams the way foresters read rings. We watch lensed arcs curve around clusters, measuring mass we cannot see. We measure supernovae to track the expansion, baryon acoustic oscillations to set the cosmic ruler, weak lensing to weigh large swaths of sky. Each method is partial. Together, they cross-check and refine, giving us the confidence to speak softly of a universe that is both comprehensible and mysterious. Inside galaxies, subtler instruments listen to subtler music. Integral field spectroscopy paints velocity maps that reveal bars and warps. Radio arrays trace neutral hydrogen beyond the bright stars, showing warps stirred by companions. Millimeter telescopes chart the cold molecular gas that will be tomorrow's stars. X-ray observatories see the hot halos where outflows deposit their heat. The result is a portrait, neither static nor chaotic, a portrait of self-regulation, punctuated by encounters, framed by the slow pressure of expansion. In the landscape of possibilities, three fates stand as landmarks. With a cosmological constant, the universe tends toward a cold acceleration. Structures that are already bound keep their company. The rest slips away. New stars become rarer. The dark becomes more pronounced. With a dynamical dark energy that weakens, gravity could reclaim more influence, altering the long tail of structure's future. Though present data tie us gently to constancy, with a phantom energy that strengthens, the very bonds of atoms would someday be threatened. The last is a cautionary poem more than a prediction. For now, all signs point to a universe that will keep spreading and cooling, while local islands continue their slow, luminous work. Even in that long view, the meaning of the present is not diminished. Galaxies are still making stars. Stars are still forging elements. Planets are still forming from disks lit by suns that have only recently ignited. The balance of forces, gravity gathering, radiation, and winds dispersing, chemistry enabling, continues to produce forms and cycles that are beautiful precisely because they are temporary and precise. It took the early universe's vigor to draw the web tight. It takes dark energy's patience to ease the web apart. Between those movements, everything familiar has room to exist, so the advanced topics resolve into something intimate. A pressure in empty space that sets the tempo of separation. A black heart in many galaxies that sets the pulse of moderation. A history of encounters that set the shape of memory. The cosmos manages itself with feedback loops and delays, with sudden meetings and long silences, with a constant exchange between what is bound and what drifts. If you imagine the universe as a night sea, dark energy is the slow tide, galaxies are the islands, mergers are the storms that reshape shores, black holes are the deep currents that keep the water turning. Star formation is the glow in beach windows as evening falls, and in that view, the evolution of everything feels less like an equation and more like a story you can fall asleep inside, where nothing is rushed and everything slowly, softly finds its place. Dark energy sets the tempo of the far future, so softly you might miss the beat unless you measure with clocks made of galaxies. If it holds steady as a true cosmological constant, space will keep widening with the patience of tide, and everything not already bound, filament to filament, cluster to cluster, will drift beyond mutual reach. Star-forming reservoirs will thin, gas will cycle into stars, and back again until there is little left to cool. The bright blue voices of youth will quiet, red embers will dominate the choir. This slow dimming is the path called heat death, or the big freeze. Not a violent curtain, but a room growing larger and colder until warmth is a local memory. In trillions of years, long after the last spirals have softened into lenticulars, and the last dwarfs have used their modest fuel, galaxies will be museums of remnants, white dwarfs cooling to black, neutron stars ticking down their spins, black holes ruling the deep night. Black holes, for a time, will be the monarchs of the late universe. They grow by feeding on gas, on stars, on other black holes, until gravity itself seems to have a face, yet even they are not eternal. Quantum mechanics whispers a loophole called Hawking radiation, a trickle of heat from horizons that should let nothing out. It is a process so slow that the word eon buckles under it. But given enough time, even supermassive black holes dissolve into a hush of photons and light particles, their mass paid back to the dark in a drizzle of energy. When the last hole has evaporated, the universe will be left to very long wavelengths, very low temperatures, and the faint arithmetic of particle decays. The clocks still tick. The music, such as it is, becomes too low to hear. All of this rests on how dark energy behaves. If it is constant, the story stretches thin and quiet. If it is not, if the pressure grows more negative with time, then the widening of space accelerates into something like panic. Structures that are now safe would be pried apart, one scale at a time. Clusters, then galaxies, then solar systems, then planets, then atoms, themselves, the Big Rip. This is not the favored reading of the data, but predictions are promises made to uncertainty. We keep them lightly, turn the knob the other way, and imagine a universe where matter and its gravitation outvote dark energy in the long run, or where dark energy weakens. Expansion stalls, reverses, and the sky begins to fall toward itself, the big crunch. Some dream one step further, a crunch that rebounds, a big bounce, a cosmos that breathes in cycles, expand, cool, contract, kindle, leaving fossils of previous beats in the pattern of new ones. These cyclic models live where quantum gravity and cosmology shake hands. The handshake is still being practiced. Between the first flame and the far ash are the fates of things that feel close. Galaxies, stars, worlds, and the quiet relics left when their burning ends. Star formation is already past its cosmic noon. The universe once made stars 10 times faster than it does now. Gas was easier to come by. Mergers were more common. Cooling was brisker. Since then, supply and demand have walked each other down. Spirals will keep making new stars for a while, hundreds of billions of years for the smallest, which sip fuel instead of gulping, but the net trend is decline. Massive stars, those fast, bright sentences, will continue to draft the heavy elements and return them to the medium, but their punctuation marks supernovae will become rarer events in a literature of aging suns. Dwarfs red and patient will carry the light late into the evening, fusing hydrogen in cramped cores for trillions of years, then fading into degenerate embers. Planets will keep their vigil as long as their suns do. Some will be flung outward by chance encounters. Some will spiral inward under tides. Some will drift in the dark as orphans. Their warmth, the memory of formation, and radioactive whispers from stone. To speak of futures with a straight face, astronomers first learn to see the past as it really was. Light travels at a finite speed. Every distant object is a time machine. Observational astronomy is the craft of turning those echoes into chronologies. The core instrument is the telescope, a patient collector of light now built in many flavors and stationed on mountaintops, deserts, balloons, airplanes, and in orbit above the weather of air. What telescopes gather Spectroscopy interprets light fanned into its wavelengths so that elements can sign their names in narrow lines. Hydrogen writes alpha. Sodium leaves a doublet. Oxygen glows in green. Even molecules CO, H2O carve patterns that can be read. From these signatures, we deduce temperatures, densities, chemical abundances, pressures, motions, and the Doppler shift spectral lines nudged red or blue tells us the speed of approach or recession. The systematic redshift of distant galaxies was the first clear sentence in the story of expansion. More precise measures of redshift across vast samples now trace the growth of structure and the ruler marks of baryon acoustic oscillations impressed in the early plasma. Space telescopes widened the aperture of time. The Hubble Space Telescope gave us deep fields where thousands of galaxies bloom in a patch of sky so small it could be hidden by a grain of sand at arm's length. Statistical time capsules showing how forms change with redshift. Its successor in the infrared, the James Webb Space Telescope, reaches further back into the stubborn redness of the first luminous structures. Where dust once blinded us, we see through. Where expansion stretched light beyond Hubble's reach, Webb catches it again. Together they show starburst knots in toddler galaxies, bars forming early, disks settling sooner than we guessed, and black holes bright and busy before a billion years had passed. From the ground, new tricks undo old limits. Adaptive optics watches the twinkle imposed by the atmosphere and bends a mirror in real time, hundreds or thousands of times per second, to cancel it, sharpening stars to near space clarity. Interferometry yokes multiple telescopes into one synthetic eye, with the resolving power of a mirror as large as the separation between them. The Very Large Telescope weaves beams across baselines to discern structures in disks where planets are forming. ALMA stitches antennas to map cold dust and molecular gas with tender detail. Radio arrays link across continents in very long baseline interferometry to sketch the silhouette of a black hole's shadow. Radio astronomy listens where the night is bright with whispers. Neutral hydrogen's 21-centimeter line maps, streams, and warps far beyond the optical disc. Pulsars mark time with millisecond exactness. Vast radio bursts spark puzzles. The cosmic microwave background hums its near-perfect blackbody tone with minuscule hot-cold freckles that encode our first conditions. Even larger ears are coming. The square-kilometer array will net vast swaths of radio sky, charting hydrogen across cosmic history, testing gravity with pulsar timing, and listening for the low-frequency waves of merging giants. The Gaia mission is measuring the positions and motions of billions of stars with a precision that remakes the Milky Way as a moving sculpture. Streams pop into focus. The disk's warp becomes measurable. The bar's pattern speed becomes a number instead of a rumor. Transit missions like Kepler and TESS watch the slight, regular dimming of stars as planets cross in front tens of thousands of worlds, many unexpected, their orbits and sizes telling us how easily nature makes systems unlike ours. All of this seeing produces oceans of numbers. Computational astronomy is the ship we sail on them. Simulations that evolve billions of particles under gravity, hydrodynamics that follow gas as it cools, collapses, forms stars, launches winds, subgrid recipes that mimic the unresolved physics of feedback, radiative transfer that turns matter back into light as an observer would see it. On the other flank are inference engines, Bayesian frameworks, and machine learning tools that fit models to data, uncover patterns in spectra, separate overlapping sources in confused fields, and flag anomalies that may be new kinds of objects. The dialogue runs both ways. Observations calibrate simulations. Simulations suggest where to look next and what questions to ask of the data we already have. Telescopes themselves are lessons in patience. Refractors begin with a lens, glass shaped to bend parallel rays toward a focus. They are simple, crisp, and because lenses sag and colors spread limited in size, reflectors use mirrors. A large, carefully figured primary reflects light to a secondary and then out to a camera or eyepiece. Mirrors can be bigger, and they can be stacked in segments that act as one. Their shape can be nudged live by actuators to hold the perfect curve as the night breathes cold, resolving power scales with diameter. Double the size, and you can separate things closer together on the sky. Collect 4 times the light, and you see fainter still. Modern observatories add coronagraphs to blot out starlight and reveal exoplanets. Integral field spectrographs to record a spectrum at every pixel, and laser guide stars to seed adaptive optics where no bright star is near. The last century has been a cascade of astonishments. The expansion of the universe redefined our address and our sense of time. The discovery of the CMB clinched the hot beginning and gave us a baby picture with enough detail to weigh ingredients and take the universe's temperature. The first dynamical black holes, Cygnus X, one among them, moved theoretical curiosities into the catalog of neighbors. The first exoplanets upended our parochial instincts. The inventory since has shown systems with hot Jupiters skimming their stars, compact trains of super-Earths, worlds in binary systems, atmospheres already being read line by line. Space telescopes, Hubble, and now Webb made the far familiar. Ground giants with adaptive optics matched their sharpness. And then space-time itself became observable. Gravitational waves rolled past from merging black holes and neutron stars, carrying not just energy, but stories that no photon could tell. With each discovery, theory stretched and found new footing. It builds models of inflation to explain the smoothness and spectrum of primordial fluctuations. It writes down dark matter candidates and follows their implications for structure on small scales. It parameterizes dark energy and tests whether it deviates from a constant. It treats galaxies as ecosystems with inflows, outflows, and star formation laws. It studies the torque of bars, the resilience of disks, the ways mergers redistribute angular momentum. It solves the magnetized turbulence that seeds star formation in clouds and the nuclear reaction chains that turn protons into sunlight. It solves Einstein's equations for colliding black holes and predicts the precise chirps that LIGO would later hear. It speculates carefully, and then it submits to data. Some futures are not cosmological, but practical. The future of how we will know. Arrays that will map the 21-centimeter line across huge fractions of the sky promise a tomography of the cosmic dawn, turning reionization from a cartoon into a movie with timestamps. Next-generation optical surveys will scan the sky nightly, catching transients by the millions, assembling light curves for supernovae that pin expansion more tightly, and finding the odd and the rare, the weird, which more than once has been the door to the next theory. More sensitive gravitational wave detectors will hear the background hum from countless distant mergers and perhaps the basso continuo of the early universe itself. Neutrino and cosmic ray observatories will add their sparse, high-energy syllables. Each new window will reveal surprises. Surprise is not failure, but growth. Against these grand arcs and instruments, it is easy to feel small. That feeling is correct and also incomplete. The predictions we make, big freeze, big rip, big crunch, big bounce, are not assertions of control but expressions of intimacy with the laws we see at work, the same laws that turn dust to planets and seawater to song. The fate of stars is the slow extension of the hydrogen fusion that warms your skin. The evaporation of black holes is quantum field theory in a curved space, a marriage of principles we already use to make lasers, transistors, and MRI machines. The telescopes are bigger than cathedrals, but their purpose is homely, to bring far things near enough to be folded into thought. So the likely future is a universe that keeps expanding under the quiet pressure of dark energy, in which the spaces between islands grow as the islands themselves continue to evolve internally, merging when bound, fading when starved, living out the long coda of stellar remnants and the longer coda of black holes. But even if this is the melody, the harmony still has room for modulation. Unknown particles, new fields, subtle changes in gravity at vast scales. We leave room because the past 100 years have rewarded humility. We also leave room because we are built for wonder. Sleep better when the next page is not fully written. Meanwhile, our craft improves. We will map the Milky Way's streams until its mergers are as obvious as rivers on a terrestrial atlas. We will weigh exoplanet atmospheres for biomarkers, the way we weigh a breeze by how it fills a sail. We will model star-forming clouds with such fidelity that the scatter about the star formation law becomes a clue instead of a nuisance. We will set better bounds on dark matter's softness or bite by the density of dwarf galaxies' cores and the survival of thin stellar streams. We will test the constancy of dark energy in ever finer redshift bins. We will ask whether the Hubble constant's present tension is an error bar misread, a calibration waiting its fix, or a sign that the early and late universe do not consult the same ledger. If the universe ends in silence, it will not do so without telling us how to listen. If it cycles, it will leave fingerprints. If it rips, there will be warnings in the way bound structures strain. And if it surprises us with an option we have not yet sketched, we will be ready. Because the practice of prediction is not prophecy but preparation, making models, building instruments, training ourselves to recognize signal in noise. That practice has already delivered the centennial harvest. Expansion, background radiation, black holes, exoplanets, gravitational waves. It will deliver more. Between the first light and the last lie, all our evenings, we live near a yellow star that burns calmly. Our planet sits in a winterless niche where water can wander between sea and cloud and snow. Our galaxy gives us a stable suburb to think in. We turn that stability into telescopes, spectroscopy, interferometers, supercomputers, and equations that hold even when the room changes scale by factors of 10 to the 26th. That, too, is a prediction of the future, that we will keep asking, keep building, keep listening. The rest, heat, death, or bounce, rip or crunch, will be what it will be. In the meantime, the night is full of reachable light, and the story still wants telling. At their quietest, the best theories feel like lullabies written in mathematics, lines and curves that hum beneath everything. From the jitter of an electron to the slow turning of a galaxy's arms, they do not shout, they breathe. And as they breathe, they hold the room steady so we can fall asleep inside the truth. When we speak of models, we are not only speaking of equations, we are speaking of a way of listening to the universe, of letting it tell us how it prefers to move, how it chooses to bind and unbind, how it becomes structure Out of silence, the standard model sits close to the pillow. A compact map of the particles and forces that make ordinary matter behave. Quarks link arms to form protons and neutrons. Leptons flicker at the edges. Gluons glue. Photons carry light's gentle push. And the heavy W and Z bosons handle the strange arithmetic of the weak interaction. For decades, this map had a blank space where a lantern should be. The equation said there must be a field everywhere, invisible as air and yet unavoidable, that gives many particles their mass as they wade through it. We waited, and then in 2012, the tunnel deep beneath the Alps whispered back. A bump in the data, small and sure. The Higgs boson waving from the fog. It was not fireworks so much as relief. A soft click as a key slid home. Suddenly, the rules of the very small felt less like guessing and more like memory. And yet that tidy map has edges. It leaves gravity outside the door, like rain on a coat. It does not name dark matter or dark energy, the deep ingredients we taste in the motions of galaxies and the widening of space. The standard model is a good nightlight, not the dawn. To understand the weight that keeps planets faithful to their orbits and the softness that pulls the horizon farther away with time, we turn to another book on the nightstand, Einstein's General Relativity, a way of thinking in which mass and energy bend the stage beneath our feet. In this telling, gravity is not an invisible string tugging on marbles. It is the curvature of space-time itself, a slope and swirl that every object follows because the path of least resistance is no longer straight. Light remembers this, too. It bows around clusters of galaxies, its path arcing just enough that distant objects appear smeared or multiplied, as if seen through water. The orbit of Mercury nods to this curvature. The silhouettes of black holes confirm it with a dark ring where even light cannot return. And in the trembling of space itself, we heard relativity sing the little chirps of gravitational waves from colliding black holes and neutron stars, ripples crossing us after traveling for 100 million years, like faint thunder from a storm we only now perceive. Between the small and the large, models become choreography. The lambda cold dark matter picture is the soft metronome at the back of the orchestra. Lambda for the pressure of the vacuum that makes expansion accelerate. Cold dark matter for the unseen mass that clumps early and invites gas to follow. Start with a nearly uniform universe. Stir it with little primordial ripples, and the equations grow filaments of invisible scaffolding. Along those filaments, gas cools and condenses. Stars kindle, and galaxies assemble at the nodes like cities forming at the crossroads of rivers. When we compare this simulated web with what telescopes reveal the spacing of clusters, the way galaxies cluster, the delicate pattern etched on the cosmic microwave background, there is a quiet consonance. Not perfect, never perfect, but close enough to trust and far enough to keep us curious, to explain why the universe looks so even, so flat, and yet still modeled with just enough seeds for structure. Many theorists speak of cosmic inflation, a sudden, early expansion that smoothed the wrinkles and stretched quantum fluctuations into the first threads of the web. It is a bold idea with many dialects. We have not yet caught its signature directly, but the sky otherwise behaves as though something like it happened. The microwave background is too uniform, the geometry too near flat, the spectrum of tiny density variations too gentle to have arisen without some very early breath. We keep listening for its Polaroid fingerprint in the polarization patterns of ancient light, a delicate twist like frost on a window, the kind of detail you can only see when the air is still and the instrument is patient. All of this, The Standard Model's neat taxonomy, relativity's curved stage, lambda CDM's steady beat, inflation's first gusts points toward a method as much as a result. Theories predict where to look. Observations return with riddles. Simulations play them both against each other until the notes agree. In that spirit, computational universes have become a common dream. We set the initial conditions, like laying out the pieces on a board: how much dark matter, how much ordinary gas, how fast the early universe hummed, and then we press go and watch a billion years pass in an hour. Gravity binds, hydrodynamics cools, shocks ripple through forming disks. Feedback from newborn stars and supermassive black holes blows cavities and carves channels. Metal-rich gas rains back down. Adjust a single knob, the efficiency of star formation, the strength of supernova winds, the appetite of a central black hole, and you can change a galaxy's fate from a quiet spiral to a quenched elliptical, or something between. By comparing these virtual histories with the starlight, we actually see the colors, the gradients, the motions. We learn which recipes are merely clever and which are close to true. When we model the birth of galaxies more closely, we find dark matter drawing the first lines like a charcoal sketch. Halos form where the invisible material clumps, and into those wells gas falls, heats from compression, then cools by shedding light in lines that tell us which atoms are present. Cold rivers of gas thread the halos and drizzle onto disks, keeping star formation alive like a slow rain. Within the densest clouds, turbulence and magnetic fields argue with gravity until gravity finally wins and collapses a knot into a star. That star lives fast or slow depending on its mass, and when it dies, it returns momentum and metals to the medium, adding wind to the city's weather, adding carbon and oxygen to the ingredients for future planets. In a few galaxies, gas tumbles inward to a central black hole. It feeds and brightens and coughs out jets and radiation that can press on the surrounding material, heating it, lifting it, sometimes preventing it from cooling into yet more stars. This is not destruction. It is regulation. It is how the galaxy avoids burning through its pantry in one long summer. Simulations make these cycles visible on the screen, but they grow honest only when the sky says yes. We check the shapes of rotation curves and the thickness of disks, the color distribution across cosmic time, the metallicity gradients in spirals, the mass of central black holes, and the calmness or clamor of their neighborhoods. We verify that massive clusters house hot halos that glow in X-rays, that dwarf galaxies have been easy to harass and strip, that satellite systems wrap around hosts in streams like chalk marks in a dance studio. We nudge the small-scale physics of star formation so the global relation between cold gas and star birth emerges naturally. Not as a coincidence, we refine black hole feedback until it suppresses star formation just enough in massive galaxies, without overcooking the circumgalactic medium that telescopes now observe in absorption against background quasars. Every match is a breath out. Every mismatch is a reason to brew more coffee. While we refine, the mysteries keep watch. Dark matter reveals itself by the way galaxies spin too quickly at their edges, by the way clusters need more mass than starlight supplies to hold together, by the way gravity lenses background galaxies more strongly than visible matter alone can explain. The candidates line up like actors waiting to audition, weakly interacting massive particles, axions wavering gently like fields, sterile neutrinos, particles that collide with themselves just enough to soften the cores of dwarfs. Detectors, buried under mountains, listen for the faintest taps. Colliders revisit the high energies of the early universe. Stellar streams are mapped with exquisite precision to see if an unseen clump has perturbed them. So far, The answer is a smile and silence. We infer dark matter by what it does, not by what it is, and that is both frustrating and fertile. Dark energy is subtler still. It seems to fill space uniformly, a pressure with negative sign that urges expansion faster rather than slower. If it stays constant, galaxies, not already bound, will slip slowly beyond the circle of one another's influence. Night will thin. If it evolves, it may leave a different signature in how structure grows, in how standard candles dim with distance, in how the cosmic ruler, those small ripples frozen into matter when the universe was young, spreads with time. We measure and remeasure. We compare the expansion rate inferred from the early universe, etched into the microwave background, with the rate measured from the nearby universe, derived from precise distances to supernovae and variable stars and masers. The two answers do not quite meet in the middle. The Hubble tension sits like a pebble in the shoe. It might be a calibration story with a patient ending. It might be the first hint that something in our simple picture is a little more complicated. Either way, the models keep room for correction. Good maps always leave room at the edges for the next trail. The puzzle of our beginning remains tender. Inflation offers a coherent preface, but not yet a single compelling author. Some versions predict ripples in polarization we have not found. Others sit quietly beneath detection for now. We look with care because the sky is full of foregrounds, dust that glows and polarizes on its own, magnetic fields that twist the narrative, and the signal we seek is a whisper behind the wind. If we find it, we will glimpse the energy scale of the first instant. If we do not, we will learn how gentle that first breath must have been. Then there is the question of why anything persists to ask questions. If the Big Bang had made matter and antimatter in perfect equality, the two would have annihilated each other into pure light and left little to assemble into stars or stories. Something about the laws allows a small imbalance. Three conditions, simple to list and hard to implement, must be met for the universe to prefer matter. We have seen hints of this preference in the decays of certain mesons, little asymmetries that say nature is not perfectly ambidextrous, but the degree we have measured is not large enough to account for the sum we see. Perhaps neutrinos hold a larger asymmetry, their own kind of matter-antimatter patterning that tipped the balance early on. Perhaps other fields, hidden in the dawn, did the bookkeeping for us. We keep looking for rare decays, for neutrinoless double beta processes, for the tiny tilts that betray a larger lean. If theoretical models are the story's grammar, simulations are the rehearsals, and observations are the performance. In one corner of this rehearsal room, disks of dust spin around young stars in the Orion of another galaxy. Within them, pebbles collide, grow, and drift inward. Ice lines divide chemistry into zones. Nascent planets perturb the gas into rings and gaps we can now resolve with millimeter eyes. In another corner, two galaxies pass close. Tides pull out long tails. Star formation flickers in compressed knots. The cores spiral together, and the central black holes approach in a slow, stately dance whose final step will ring space-time like a bell. Far above it all, at the nodes of the largest web, clusters of thousands of galaxies swim in a sea of thin, hot plasma. The imprints of their growth show up in the way they dim the microwave background as photons pass through subtle shadows that say mass and heat are present, just as the model foretold. To keep this choir in tune, we refine the instruments that link math to sky. We observe the faint absorption lines of the circumgalactic medium to understand how galaxies inhale and exhale. We map neutral hydrogen in emission at the edges of disks to see warps triggered by satellites. We time pulsars to make a galactic scale detector for the slowest gravitational waves. We use integral field spectroscopy to watch gas move within galaxies, pixel by pixel, and to understand how bars feed bulges and how outflows choose their escape routes. We measure the chemical abundance of stars across the Milky Way to reconstruct its mergers, as an archaeologist would reconstruct a city from broken pottery. We ask the dark whether it is cold or warm or self-interacting by seeing how many small satellites survive and how dense their cores have grown. Every success tightens the weave. When we forecast the abundance of galaxies by mass and color, and the sky hands back numbers within reach of our prediction, we sleep easier. When we predict the temperature of cluster halos and find that X-ray maps agree, we exhale. When we run the clock forward and see disks regrow after mergers to become spirals again, and telescopes find examples of exactly such regrown spirals, we nod because the universe likes second chances. When discrepancies arise, two chord dwarfs, two little variants, lensing anomalies, we resist the urge to force the fit. Sometimes the physics of feedback, honest but complicated, can reconcile the difference. Sometimes the difference is the seed of a changed premise. Either way, models earn trust not by being untouchable, but by being corrigible, like a skilled musician who can retune while playing. Behind the precision and the data tables is a quiet ethic. Theories are promises to the sky that we will be ready to hear what it says. The standard model promised that a field would be found. The sky obliged. Relativity promised that gravity bends light and that space-time rings. The sky obliged. Lambda CDM promised a web, a particular pattern of modeling in the ancient light, and a rate of structure growth tied to that pattern. The sky obliged with subtle caveats. Inflation promised an almost flat universe, sprinkled with nearly scale-invariant fluctuations. The sky obliged with an open question about the exact shape of the first inflationary flute. Each time, we update the score. Each time, the music is a little clearer. As we drift, it helps to remember that models are not cages. They are lanterns that throw enough light to walk safely, even if the edges of the path are still soft. When a new survey reveals a population of galaxies that formed their bars earlier than we thought possible, we do not abandon the lantern. We trim the wick. When a quasar shows a black hole, too massive, too soon, we do not curse the grammar. We add a clause about gas flows and seeds and special environments in the early night. When a measurement of the Hubble constant disagrees with another, we do not cover our ears. We listen for the squeak in one instrument or the hidden harmony in a deeper theory. In the end, the power of theoretical models is not that they lock the future in place, but that they let us rest in a world that is comprehensible while still being wonderfully unfinished. Mathematics gives us the shapes of possibilities. Physics tells us which shapes the universe prefers. Observation chooses among them, with the authority of light that has traveled for eons to arrive tonight. Between those three, a triangle as steady as any constellation, we find enough certainty to build and enough mystery to keep building. And in the soft hours, when the house is quiet and the sky leans at the window, the models become what they have always been, a way to let the mind float on the night sea without losing sight of shore, a way to feel the deep structure of things without clenching, a way to translate the universe's patient breathing into stories that hold until morning. The question of whether our universe is alone drifts somewhere between science and dream, an open window through which both curiosity and wonder lean in. If space truly stretches without end, perhaps creation does not stop at the edge of what we can see. Perhaps, beyond the faint horizon of our cosmic bubble, There are others whole realities, quiet or chaotic, built on different notes of the same cosmic song. This is the heart of the multiverse theory, a notion that feels both dizzying and intimate, that what we call the universe might be only one room in a far larger mansion of existence. The idea took shape not in fantasy, but in the equations of cosmic inflation, that brief, furious instant after the Big Bang when the universe expanded faster than light could travel. Some versions of inflation do not end everywhere at once. They keep bubbling outward, with regions stopping their expansion at different moments. Each finished region cools and settles, becoming its own self-contained universe, sealed from its neighbors by an impassable gulf of space. In this eternal inflation picture, our universe is one bubble floating in an infinite foam of universes, each with its own beginning, its own timeline, its own physics whispering, its own rules. Another doorway to the multiverse opens through string theory, a framework that replaces the smallest known particles with tiny, vibrating loops of energy. The way each string vibrates defines what it becomes: a photon, an electron, a quark, and the mathematics of these vibrations allows for an immense landscape of possible universes. Each solution in that landscape is like a distinct world with its own arrangement of forces, constants, and dimensions. In some, gravity might be stronger or weaker. In others, atoms might never form, or stars might ignite in a completely different way. If this cosmic landscape truly exists, then our universe is not the rule, but one of countless variations. A single note in a vast cosmic chord, the anthropic principle offers a quiet reflection within this immensity. It suggests that we find ourselves in a universe whose physical constants seem fine-tuned for life, not because of divine chance, but because we could only exist in such a place. If billions of universes bloom with different conditions, then it is unsurprising that one ours happens to host the fragile chemistry of consciousness. The multiverse, in this view, turns the improbable into the inevitable. Yet for all its elegance, the multiverse remains a theory wrapped in mist. Its very nature, worlds forever disconnected from ours, makes it almost impossible to test. There are no telescopes that can peer into another universe, no signal that can cross the border between bubbles, and so the idea lingers on the threshold between physics and philosophy, between what can be proven and what can only be imagined. Still, it reminds us of something deeply human, that even at the edge of knowledge, we continue to wonder, to reach beyond the veil, and to dream of other skies quietly shining beyond our own. Gravity moves through the universe like a quiet hand, unseen yet unyielding, shaping everything it touches. It is the weakest of the fundamental forces, yet it is the one that never lets go, the patient sculptor of stars, galaxies, and time itself. According to Einstein's vision, gravity is not a tug or a pull, but a bending of the fabric of space-time. Mass tells space how to curve, and space tells mass how to move. Every orbit, every falling leaf, every dance of galaxies is simply matter, following the lines drawn by that invisible curvature. In the newborn universe, gravity was the artist that found pattern in chaos. After the Big Bang, the cosmos was a near uniform sea of energy and particles, shimmering with faint ripples, tiny irregularities in density that would become the seeds of everything. Gravity amplified those ripples, pulling matter together into clouds, clouds into stars, and stars into galaxies. From this gentle clustering came the great web of the cosmos, threads of galaxies strung along invisible filaments of dark matter, each one humming with the memory of that first gathering. Though dark matter emits no light, its gravitational influence defines the structure of the universe, tracing the hidden scaffolding upon which everything visible now rests. Gravity does not rest. It weaves galaxies into families, groups, clusters, and superclusters, connected by tendrils that stretch across unimaginable distances. Sometimes its work is serene. Sometimes it is spectacular. When two galaxies drift too close, gravity draws them together in a slow, luminous embrace. Their stars rarely collide, but their gas clouds crash and compress, igniting bursts of newborn light, entire generations of stars born from the meeting. Our own Milky Way is moving towards such a union with Andromeda, a silent journey that will take 4 billion years. When the two merge, their spirals will dissolve into a new elliptical form, and gravity will once again have reshaped the sky. Yet even this master force does not act alone. On the grandest scales, it wrestles with its opposite dark energy, the mysterious pressure that drives the accelerated expansion of the universe. Gravity gathers, dark energy scatters. Between their pull and push lies the fate of all things, whether the cosmos will expand forever, thin and cold, or one day slow, fall inward and fold into itself again in a cosmic sigh. Gravity is also the heartbeat of stars. It squeezes clouds of gas until their cores ignite in fusion, the same process that fills our nights with starlight and our worlds with the elements of life. When a star's fuel is gone, gravity decides its ending: a peaceful cooling, a brilliant explosion, or collapse into a black hole where space-time itself folds inward. Even here, in the soft pull of ocean tides beneath the moon, we feel its constant rhythm. It binds the vast and the small, the infinite and the intimate, reminding us that everything, from galaxies to grains of sand, moves in the same quiet curve of belonging. Gravitational lensing is one of the most elegant demonstrations of how gravity bends not only motion, but vision itself. It transforms the cosmos into a living experiment where light, the universe's oldest messenger, follows curved paths through the invisible architecture of space-time. When a massive object, such as a galaxy or a cluster of galaxies, lies between us and a more distant source, its gravity warps the space around it. Light from the faraway object travels along this curved space-time, arriving at Earth bent and distorted. To our eyes in telescopes, that distortion becomes a natural magnifying glass, a lens made not of glass, but of gravity itself, predicted by Einstein's general relativity and first confirmed during the 1919 solar eclipse. Gravitational lensing revealed that gravity could bend starlight just as surely as it could guide planets. Over a century later, it remains one of astronomy's most powerful tools, allowing us to peer farther into the universe than any human-made telescope could alone. When the light of a galaxy billions of light years away passes near a closer galaxy cluster, the cluster's gravity can magnify the background light, revealing the structure of galaxies from an era when the universe was still young. These cosmic lenses act as amplifiers, bringing the faint glow of ancient starlight into focus. Through them, astronomers can study how the first galaxies formed, how fast they made stars, and how their structures evolved across cosmic time. Yet lensing does more than reveal beauty, it unmasks the invisible. Because dark matter does not shine or absorb light, its presence would be undetectable were it not for gravity's subtle fingerprint. When astronomers observe how light bends around clusters of galaxies, they find far more gravitational influence than visible matter can account for. The extra bending maps the distribution of dark matter itself, allowing scientists to chart the hidden scaffolding of the cosmos. Through weak lensing, where the distortion is small but statistically measurable, researchers can trace the large-scale structure of the universe, the cosmic web across billions of light years. Lensing appears in many forms. Strong lensing produces spectacular visual echoes, Einstein rings, luminous arcs, or even multiple images of the same galaxy stretched across the sky. Weak lensing works more quietly, warping the shapes of countless distant galaxies, just enough to betray the mass in between. And microlensing, the gentlest form, occurs when a single star or planet drifts in front of another, causing a brief but measurable flicker in brightness. This fleeting shimmer can reveal exoplanets orbiting distant stars or compact, unseen objects like rogue planets and black holes drifting through the Milky Way. In this way, gravitational lensing becomes both a map and a message, a reminder that the universe is interconnected through invisible threads of gravity. It allows us to study dark energy's role in cosmic expansion, to weigh galaxies by the curves of their light, and to glimpse the distant past through nature's own telescope. In bending light, gravity lets us see the shape of the unseen and invites us to wonder what else the cosmos may be quietly revealing. Black holes are among the most extraordinary and mysterious phenomena in the universe. Cosmic paradoxes where gravity becomes so intense that even light cannot escape. They are not merely exotic objects. They are the ultimate expression of Einstein's theory of general relativity, where the geometry of space-time folds in on itself. At their heart lies a singularity, a point of infinite density and zero volume, where the known laws of physics cease to function and our understanding of reality reaches its limit. Most black holes begin life as the remnants of massive stars. When a star at least 3 times the mass of the Sun exhausts its nuclear fuel, the outward pressure from fusion that once held gravity at bay vanishes. The core collapses under its own immense weight, and if it is massive enough, nothing can halt this inward fall. Space itself curves inward until a boundary forms the event horizon, the point beyond which escape is impossible. Anything crossing this threshold, matter, radiation, even information, disappears from the observable universe, its fate sealed by gravity's relentless pull. Black holes come in many sizes. Stellar black holes, formed from collapsing stars, typically range from a few to dozens of solar masses. Intermediate black holes, hundreds or thousands of times more massive than the Sun, may form through the merging of smaller black holes or the collapse of enormous gas clouds. At the largest scale lie supermassive black holes, giants with millions or even billions of solar masses. These titans dwell at the centers of galaxies, including our own Milky Way, where Sagittarius A times quietly exerts its gravitational dominance. How such behemoths form remains one of modern astrophysics' deepest mysteries, though they may grow over billions of years through the accretion of gas and the merging of smaller black holes. When black holes feed, they can transform their surroundings. As matter spirals toward the event horizon, it forms an accretion disk, a whirling maelstrom of gas heated to millions of degrees. Magnetic fields twist and funnel some of this energy into powerful jets of plasma that shoot out from the poles at near light speeds. These jets can stretch across thousands of light years, influencing star formation in nearby regions and regulating the growth of their host galaxies. Despite their dark nature, black holes can be among the brightest objects in the cosmos, their violent appetites lighting up the night through X-rays and gamma rays. And yet, even black holes are not eternal. In 1974, Stephen Hawking proposed that quantum effects near the event horizon cause black holes to emit faint radiation, now known as Hawking radiation, over unimaginable timescales. This process slowly saps a black hole's mass, causing it to evaporate. For stellar or supermassive black holes, this evaporation takes longer than the current age of the universe, but it provides a vital bridge between the realms of general relativity and quantum mechanics, a glimpse toward a unified theory of physics. If black holes represent the universe's extremes of destruction, life represents its capacity for creation and balance. The conditions necessary for life, as far as we understand them, rely on a delicate interplay of chemistry, energy, and stability. At the core of this is the habitable zone, the narrow region around a star where temperatures allow liquid water to exist. On Earth, water is the solvent that enables complex chemistry, the medium where carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur combine to build the molecules of life. An atmosphere plays a similarly crucial role. It moderates temperature, shields against cosmic radiation, and maintains the gases essential for metabolism. On our planet, oxygen sustains respiration, while carbon dioxide drives photosynthesis, anchoring the balance of ecosystems. The source of energy is equally vital. On Earth, sunlight fuels life through photosynthesis, but discoveries of hardy organisms in deep-sea hydrothermal vents have revealed that life can also thrive without sunlight, drawing energy instead from chemical reactions, a process known as chemosynthesis. This insight expands the potential for life in seemingly hostile environments across the cosmos. Stability is the final ingredient. Planets with consistent climates, stable orbits, and protective magnetic fields create the calm necessary for life to evolve. Wild fluctuations in temperature or radiation could easily sterilize a world before life takes root. Earth's magnetic field and relatively stable orbit have shielded it for billions of years, nurturing the diversity we see today. As astronomers peer beyond our solar system, they search for exoplanets, worlds orbiting distant stars that might share these life-friendly traits. Thousands have been discovered, and a growing number lie within their stars' habitable zones. Space telescopes such as Kepler, TESS, and the James Webb Space Telescope now allow scientists to study these planets' atmospheres, searching for signatures of water, oxygen, methane, or other biosignatures that might hint at life. The question of whether life exists elsewhere in the Milky Way remains unanswered, yet it feels increasingly possible. The sheer number of stars, over 200 billion in our galaxy alone, suggests that life's spark may not be unique to Earth. Whether it thrives beneath the icy crust of Europa, in the clouds of Venus, or on a distant Earth-like world orbiting another sun, the search continues. In this vast, expanding cosmos, black holes remind us of the universe's power to compress everything into nothingness, while the possibility of life reminds us that even within that darkness, the universe finds ways to create and to wonder. Our galaxy, the Milky Way, is a vast, spiraling expanse containing hundreds of billions of stars, each a potential sun for its own family of planets. Among these, countless worlds orbit quietly in darkness, some barren and hostile, others perhaps warm with oceans and skies. The discovery of exoplanets, planets beyond our solar system, has revolutionized our understanding of the cosmos. Once, Earth seemed singular. Now, we know that planets are the rule, not the exception. Since the first confirmed detection in 1992, astronomers have cataloged over 5,000 exoplanets, with many more candidates awaiting confirmation. Each discovery deepens the sense that our galaxy is alive with worlds and perhaps with life. The search for habitable planets begins with the so-called habitable zone, or Goldilocks zone, the region around a star where temperatures allow liquid water to exist. Yet, habitability is not defined by distance alone. A planet's atmosphere, magnetic field, and geological activity are equally crucial. A thick atmosphere can trap heat, circulate gases, and shield against deadly radiation. A magnetic field generated by a planet's molten core protects its surface from solar winds that might otherwise strip away that atmosphere. Meanwhile, geological activity, volcanism, and plate tectonics recycles carbon and minerals, stabilizing climate and creating niches where life might thrive. Astrobiology, the science that explores life's possibilities beyond Earth, weaves together astronomy, biology, chemistry, and geology. By studying extreme environments on our own planet, from volcanic vents on the ocean floor to frozen Antarctic lakes and acidic hot springs, scientists learn how resilient life can be. These extremophiles thrive in crushing pressures, blistering heat, or toxic chemical soups, suggesting that life elsewhere may flourish under conditions once deemed impossible. If microbes can survive beneath kilometers of Antarctic ice or within rocks on the seafloor, perhaps they can also endure beneath Mars's rusty sands or within the icy oceans of Jupiter's moon Europa. One of the most promising tools in the hunt for extraterrestrial life is atmospheric spectroscopy. When a planet passes in front of its star, a small fraction of the starlight filters through the planet's atmosphere. By analyzing this light, scientists can identify chemical fingerprints of gases such as oxygen, methane, and water vapor. On Earth, these molecules are tightly linked to biological activity. Detecting a similar combination on another world would not prove life exists, but it would be one of the most compelling clues in cosmic history. The James Webb Space Telescope and next-generation observatories are already peering at exoplanet atmospheres, seeking these subtle signs of alien biospheres. Closer to home, the search continues across our own solar system. Mars has long been a prime candidate. Its ancient river valleys and sedimentary rocks suggesting it once hosted liquid water. Robotic explorers like Perseverance and Curiosity analyze its soil for traces of organic molecules and potential microbial fossils. Beyond Mars, the icy moons, Europa and Enceladus, captivate scientists with evidence of global subsurface oceans. Geysers on Enceladus have been observed spewing water vapor and organic compounds into space, hinting at chemical conditions similar to Earth's hydrothermal vents, places where life may have begun. Future missions aim to drill through these icy crusts to sample the hidden seas below. The search extends even further to Titan, Saturn's largest moon, whose thick atmosphere and methane lakes make it one of the most Earth-like worlds in the solar system, albeit in a frigid, alien way. Here, scientists speculate that exotic forms of chemistry could support life based on methane rather than water, challenging our Earth-centric notions of biology. Each mission to these worlds expands our understanding of what habitable truly means. While microbial life represents one frontier, another question looms larger and older. Could there be intelligent life elsewhere? The search for extraterrestrial intelligence, SETI, seeks to answer this by listening for signals that nature could not produce structured, repetitive, or mathematical patterns in radio or optical wavelengths. Radio telescopes scan the skies for artificial transmissions, while new methods search for technosignatures, evidence of advanced technologies, such as laser pulses or megastructures that might dim a star's light in measurable ways. So far, no confirmed signals have been found, but the silence does not imply solitude. The universe is vast beyond comprehension, and our listening has barely begun. At the same time, researchers study meteorites and interstellar dust for hints of life's ingredients. Some meteorites from Mars contain complex organic molecules, carbon-based compounds that, while not proof of biology, suggest that the chemistry of life may arise naturally in many environments. Observations of interstellar clouds reveal similar molecules drifting between the stars, indicating that the seeds of life, the raw chemical building blocks, are widespread throughout the galaxy. Each discovery, each hint of possibility, reshapes our sense of place. The absence of direct evidence for extraterrestrial life does not mean the absence of life itself. It may only reflect the infancy of our search. Our instruments, though powerful, have touched just a fraction of one galaxy among billions. Somewhere, perhaps orbiting a dim red dwarf or hiding beneath an icy crust, microbial life may be stirring, or civilizations may be reaching out with signals we have not yet learned to hear. The search for life beyond Earth is not just a scientific endeavor, it is a reflection of humanity's deepest curiosity. It asks who we are, where we come from, and whether our story is being told elsewhere, under other suns. As telescopes sharpen their gaze and probes venture farther into the dark, we edge closer to an answer that could change everything. That life, in all its fragile persistence, is not unique to our small blue world, but a natural outcome of the universe's boundless creativity. The cosmic web feels like a hush drawn across the night, an immense, lace-fine lattice that the universe spun from its earliest breath. If we could dim every nearby star and let our eyes adjust to the deepest dark, we might sense its pattern. Bright knots where many strands meet, rivers of matter flowing along invisible roads, and broad, quiet basins where almost nothing lives. This is the backbone of the cosmos. Galaxies, clusters, and the tenuous gas between them, threaded together by filaments of dark matter, the unseen substance whose gravity composes the music to which everything else keeps time. Its origin was a whisper. In the first instant after the Big Bang, quantum ripples flickered tiny, almost shy departures from perfect smoothness. Inflation stretched those ripples like taffy, lifting the smallest wiggles to cosmic scales. When the universe cooled and light decoupled from matter, those faint imprints remained, etched into the cosmic microwave background as freckles of slightly warmer and cooler glow. Where the density was a touch higher, gravity had a head start. Over eons, that head start became a lead, and the lead became structure. Matter flowed downhill along gradients, too gentle for human senses, but irresistible, across billions of years. Dark matter supplied the scaffold. Though invisible to light, it gathers first and most, pooling into halos and sinking into strands that span hundreds of millions of light years. Ordinary or baryonic. Matter, gas, and dust, and everything that can shine follows the dark. It drifts into those wells, compresses, cools, and kindles stars. Filaments funnel this gas as if by hidden gutters, feeding the nodes where strands cross. There, gravity deepens the bowls and builds clusters and superclusters, the most massive bound structures in the modern universe. Between these avenues lie voids, expanses so empty that a single galaxy may wander for tens of millions of light years before meeting a neighbor. The web is not a drawing on space. It is space, shaped by gravity's patient hand. Within this framework, galaxies are born and taught their habits. In the crowded nodes and along the thicker filaments, galaxies jostle, interact, and merge. Their gas is heated by cluster atmospheres, stripped by motion, stirred by tides. Star-forming reservoirs dwindle. Colors drift toward older, redder hues. Shapes round out into ellipticals, records of a rougher youth. In the quieter filaments and near the edges of voids, galaxies sip from cooler streams. Disks retain their gas. Blue light from young stars laces their spiral arms. The web writes an address on every galaxy, and that address whispers its likely fate: fast growth or slow, quenched or still blooming, a symmetry born of where the cosmic currents converge. Feedback breathes through this architecture. Supernovae crackle and shove. The winds of massive stars press on their cradles. Active galactic nuclei at the hearts of some galaxies flare and whistle, heating and displacing gas across scales far beyond their tiny throats. These processes do not erase the web, they color it, regulating how quickly filaments can feed their nodes and how long disks can keep their star-forming calm. In clusters, the hot intracluster medium glows in X-rays, a reminder that some gas has been heated so thoroughly it may not cool for ages. In filaments, diffuse gas hides in a warm, hot phase, thin as prayer, waiting to be mapped more completely by the next generation of eyes. We know the web not because we can see dark matter directly, but because its gravity leaves fingerprints. Gravitational lensing, the gentle shearing of background galaxies, reveals mass in the foreground, regardless of whether it shines. The degree and pattern of this shearing trace the filaments like chalk rubbings over raised grain. The spacing of galaxies imprinted with a faint sound wave from the early universe. The baryon acoustic oscillation acts as a standard ruler, confirming how structures grew along the web as the cosmos expanded. Massive redshift surveys chart millions of galaxies into three-dimensional maps. Supercomputer simulations, seeded with the same primordial ripples, grow a virtual universe that looks uncannily like the real one. Where they differ, we learn. Where they match, we rest a little easier. Filaments are not empty bridges. They are conduits of life for galaxies. Cold streams can pour along them into halos, sustaining star formation, even as feedback gnaws at internal stores. In the busiest intersections, these streams can be cut or preheated. Galaxies, there may starve, aging into ellipticals nested in the cluster's glow. Along thinner threads, galaxies often keep their disks, their bars, their soft blue light. The web thus scripts a kind of environmental ecology: dense regions that recycle heat and quench, intermediate lanes that balance inflow and feedback, and peripheries that, left to their own quiet, keep building new stars from heaven's long arteries. Voids deserve their own lullaby. They are not simply absence. They are the negative space that throws everything else into relief. Galaxies born near their borders tend toward isolation and steady growth. Their dark matter halos are less harassed, their disks less rattled, their histories more like slow rivers than rapids. Cosmologists love voids because they respond differently to dark energy and potential tweaks to gravity. The way their emptiness expands holds clues to the laws that govern the largest scales. Even emptiness, it seems, has a voice if you listen long enough. The web continues to evolve. Dark energy accelerates the universe's expansion, stretching filaments thinner over vast times. Bound structures remain bound. Their gravity is enough to resist the widening, but the spaces between them will grow quieter, the inflow along the faintest threads dwindling. In the far future, clusters will be islands. The brightest filaments will dim. The map will blur at the edges while the cores harden into enduring cities of stars and remnants. The patterns set by early ripples will persist, but the traffic along the roads will slow until only the most local exchanges remain. To study this living lace, astronomers turn the entire electromagnetic spectrum into a set of brushes. Optical and infrared surveys catalog galaxies like beads on strings. X-ray telescopes weigh, cluster atmospheres, and sketch where filaments meet. Radio arrays trace neutral hydrogen, the cool reservoir from which stars are born, and will one day image the intergalactic filaments more fully. Ultraviolet and optical spectrographs read the thin absorption lines of the circumgalactic and intergalactic media in the light of background quasars, fine scratches on glass that reveal temperature, density, and motion along the lines of sight. Each technique is partial. Together, they compose. In the end, the cosmic web is less a thing to be seen than a rhythm to be felt. It is the slow waltz of gravity, written on an expanding stage. The way the universe chooses to distribute grace and scarcity, crowd and solitude. It teaches that structure grows from small favors given early, that environment shapes the song a galaxy can sing, that what is invisible can be most decisive. We live on one strand of this immeasurable net, in a quiet spur of a middling arm, of a spiral in a modest filament, just another thread in a loom so large it needs the night to be seen. And if you listen when the world is still, you might almost hear it. The soft, taut hum of connections spanning the dark, holding galaxies where they belong, carrying matter from silence into stars. The existence of the cosmic web, that vast lattice of filaments and voids weaving the universe together, is not speculation. It is a structure we can trace, map, and verify through multiple lines of evidence. One of the most persuasive comes from large-scale galaxy surveys, which have transformed the night sky into a three-dimensional map of the cosmos. Projects such as the Sloan Digital Sky Survey, SDSS, and the 2DF Galaxy Redshift Survey have cataloged millions of galaxies, revealing that they are not sprinkled randomly through space. Instead, they cluster in long, interconnected chains that trace the filamentary pattern predicted by simulations of dark matter. Between these filaments lie cosmic voids, immense expanses containing only a few galaxies. Together, these features outline a universe built not of uniform fog, but of a delicate, web-like structure, precisely what the theory of cosmic evolution predicts. These surveys also show that galaxies' motions are guided by invisible gravitational currents. Galaxies flow along filaments and gather at the intersections where clusters form. The pattern of their distribution matches the influence of dark matter, whose gravitational presence shapes the web despite its invisibility. Although dark matter emits no light, its fingerprints can be traced through the behavior of galaxies and through gravitational lensing, nature's own magnifying glass. When light from distant galaxies passes near a massive structure, the gravitational pull of the dark matter bends and distorts that light. By studying the resulting arcs, rings, and stretches of light, astronomers can map the mass distribution of the universe, revealing dark matter filaments otherwise unseen. The lensing patterns observed across the sky line up perfectly with the predictions of the cosmic web model, offering direct confirmation that dark matter's invisible skeleton supports the universe's visible form. Further evidence comes from cosmological simulations, where supercomputers recreate billions of years of cosmic history, starting from initial conditions observed in the cosmic microwave background, the faint afterglow of the Big Bang. These simulations evolve under the laws of physics, allowing gravity to sculpt matter across time. The resulting models show the gradual emergence of a web-like structure. Dark matter condenses into filaments. Galaxies form within those filaments, and voids expand between them. When compared to real observational data, the simulations and the actual universe look astonishingly alike. This convergence between theory and observation stands as one of modern cosmology's most beautiful successes. Even the thin, intergalactic medium, the diffuse gas filling the space between galaxies, confirms the web's existence. When light from distant quasars travels through this gas, certain wavelengths are absorbed by hydrogen atoms, leaving a pattern of lines in the quasar spectrum known as the Lyman alpha forest. Each line corresponds to a patch of gas within a cosmic filament. Together, these absorption features create a map of invisible hydrogen tracing the same filaments that bind galaxies and clusters. In essence, every quasar spectrum is a thread in the universe's grand tapestry, carrying the imprint of the web through time. The cosmic web's vastness is stretched across a stage that itself is growing. The expansion of the universe is not like galaxies rushing outward through empty space from a central explosion. Rather, it is space itself expanding, carrying galaxies with it. A familiar analogy is that of a balloon covered with dots. As the balloon inflates, every dot moves away from every other dot. No single dot marks the center of expansion. Each observer, wherever they are, sees the universe expanding equally in all directions. Evidence for this expansion began with Edwin Hubble's discovery in the 1,920 seconds that distant galaxies were receding. Their light shifted to redder wavelengths. This redshift occurs because as space stretches, so do the light waves traveling through it. The relationship between a galaxy's distance and its recession speed became known as Hubble's law, and the constant that defines this rate of expansion is the Hubble constant. Today, astronomers measure it in multiple ways, through the behavior of nearby supernovae and galaxies, and through patterns in the cosmic microwave background that reflect the universe's early conditions. However, these two approaches have revealed a puzzle known as the Hubble tension. Measurements from the early universe via the CMB and those from the local universe via supernovae do not agree, differing by a few percent. This seemingly small discrepancy could point to new physics. Perhaps dark energy evolves over time, or perhaps we need to adjust our understanding of cosmic expansion itself. The tension remains one of the most intriguing unsolved mysteries in cosmology. The cosmic microwave background radiation, discovered in 1965, provides another cornerstone of evidence for the universe's expansion. This faint afterglow, uniform across the sky, is the cooled remnant of the early universe, stretched and softened by billions of years of expansion. Its temperature and minute fluctuations reveal not only the universe's age and composition, but also how it evolved from a hot, dense plasma into the structured cosmos we see today. In the late 1,990 seconds, observations of distant Type Ia supernovae brought an astonishing revelation. The universe's expansion is not slowing down under gravity's pull. It is accelerating. This discovery implied the presence of a previously unknown energy component, now called dark energy, which seems to permeate all of space and exerts a repulsive anti-gravitational effect. Dark energy is thought to make up about 70% of the universe's total energy content, dwarfing both dark matter and ordinary matter. Its origin and nature remain among the most profound mysteries of modern science. The implications of this accelerating expansion are immense. If dark energy remains constant, galaxies will continue to drift apart forever, their light redshifting until it fades from view. Stars will burn out, and the universe will cool into darkness, an eventuality known as the Big Freeze. If, however, dark energy strengthens over time, it could lead to a catastrophic Big Rip, where even atoms are torn apart by the accelerating expansion. Alternatively, if dark energy weakens or reverses, gravity could, one day, halt the expansion and draw everything back together in a big crunch, collapsing the universe into a dense, hot state again, perhaps to spark another cosmic cycle. Despite its vast scale, cosmic expansion does not tear apart all structures. Within galaxy clusters or local groups, gravity is strong enough to overcome the pull of expansion. Our own Milky Way and the Andromeda Galaxy are bound together by their mutual gravity and are expected to merge in roughly 4 billion years, forming a single, larger galaxy. On local scales, gravity triumphs. On cosmic scales, expansion reigns. This universal stretching also affects the light we see. As photons travel through the expanding fabric of space, their wavelengths lengthen, carrying information about the rate of expansion and the age of the universe. By measuring the redshift of distant galaxies, astronomers can look back in time, observing galaxies as they were billions of years ago, when the universe was younger, denser, and more vibrant. Ultimately, the expansion of the universe defines both its history and its destiny. It explains the cooling of the cosmos, the distribution of galaxies, and the ceaseless evolution of structure. It ties the cosmic web's delicate filaments to the broader flow of space-time itself. Whether the universe ends in fire, ice, or renewal remains unknown. But one truth endures. Everything we see, the galaxies, the clusters, the filaments, and even the dark between them, is part of a single, ongoing motion. The quiet, eternal breath of the cosmos. Magnetic fields move through the universe like threads of dark silk, silent, tensile, almost invisible until something luminous brushes against them and reveals the weave. They are not decorations on the cosmic fabric. They are part of the fabric itself, stitched from planets to stars to galaxies, guiding charged particles the way a riverbed guides water. We do not see the fields directly. We see their handwriting. Light, subtly polarized. Radio whispers from electrons spiraling. Plasma flowing into delicate, collimated jets. When the night is quiet enough, you can almost imagine the universe humming along those lines. In stars, magnetism is born from motion. Deep beneath a star's glowing skin, hot, ionized gas churns and shears. This restless, conductive fluid acts as a dynamo, converting kinetic energy into magnetic energy, amplifying seed fields into complex, braided structures. On our sun, the field rises and breaks like surf, looping into space as arches that darken their footprints into sunspots. At times, the loops snap and reconnect in sudden releases, solar flares and coronal mass ejections hurling charged particles outward. Days later, Earth's sky answers with auroras, soft curtains of green and violet that sway where our own magnetic shield shepherds those particles into polar atmospheres. The same shield, the magnetosphere, deflects much of the solar wind. Without it, our satellites, power grids, and even our climate would feel the raw weather of space more sharply. Magnetism also shapes the very birth of stars. In the cold hush of molecular clouds, where starlight struggles to enter and gas lies millikelvin cold, gravity tries to pull everything inward at once. Magnetic fields complicate and refine that fall. Coupled to the partially ionized gas, field lines can support clouds against collapse along some directions, while permitting flow along others, stretching cores into filaments and setting the stage for where stars will first ignite. As a dense core contracts, the field intensifies, lines bunching like threads gathered in a fist. This tension regulates the pace of collapse, helping to decide the initial mass function of newborn stars, which will be light and long-lived, which will be heavy and brief. Around a forming star, a thin protostellar disk spins, the birthplace of future planets. Here, magnetic fields solve a vital problem: how to let gas lose enough angular momentum to drift inward and feed the infant star while the disk itself remains intact. Processes like magnetorotational instability, MRI, stir the disk, creating turbulence that transports angular momentum outward. Meanwhile, twisted field lines can launch magnetized winds and jets, narrow beams that carry excess spin and energy away at hundreds of kilometers per second. Those same outflows carve cavities in their natal clouds, slowing further infall and regulating star formation. Even the fine dust that will one day coalesce into worlds feels the field's indirect hand, experiencing a calmer, more ordered flow than gravity alone would provide. Between stars, in the interstellar medium, magnetic fields share custody of the gas with turbulence, radiation, and cosmic rays. Here, magnetism is less a single line and more a tangled skein, strong enough to guide charged particles along spiral paths through the galaxy, yet gentle enough to be reshaped by supernova shocks and stellar winds. This partnership creates an environment that regulates star formation. Too much turbulence and magnetic pressure, and clouds resist collapse. Too little, and gas collapses too quickly, burning its star-making fuel in a flash. Magnetism also steers cosmic rays, the swift-charged messengers that permeate the Milky Way, heating and ionizing gas, driving gentle outflows from galactic disks, and perhaps even powering large-scale galactic dynamos that sustain the fields themselves over billions of years. Galaxies carry magnetic fields the way trees carry sap threaded throughout, stronger along the arms of spirals, ordered by rotation and shear. In disks like the Milky Way, an alpha-omega dynamo can amplify weak seed fields into micro-Gauss-strength structures, aligning them into graceful magnetic arms that sometimes echo the spiral pattern seen in starlight. Where bars and density waves compress gas, fields intensify. Where supernovae bubble the ISM into chimneys, fields arch and loop, providing channels for gas to rise into the halo. Even on the largest scales, the cosmic web filaments likely hold faint magnetic signatures, whisper-thin and ancient, threading intergalactic space and subtly influencing how gas flows into forming galaxies. In galaxy clusters, the fields grow rough-edged and immense. Turbulence in the hot, X-ray bright intracluster medium twists and stretches magnetic lines across millions of light years. These fields shape radio halos and relics, vast, diffuse glows from electrons spiraling in magnetic fields after shocks from cluster mergers. Magnetism in clusters can suppress heat conduction, change how gas cools, and alter the course of feedback from central black holes, whose jets inflate cavities that rise like balloons through the hot plasma, redistributing energy and keeping runaway cooling at bay. In this way, magnetic fields help set the temperature and rhythm of the largest bound structures in the universe. Where do these fields come from? Some may be the descendants of tiny seed fields created by the first ionized flows, the Biermann battery effect, or birthed in the early universe through phase transitions or inflationary processes. Once present, even if vanishingly small, they can be stretched and strengthened by shear, turbulence, and dynamo action. Over time, what began as a whisper becomes a chorus, amplified by the motions of matter itself. Observations of blazar light hint at intergalactic magnetic fields, inferred by how high-energy gamma rays cascade and spread. If confirmed, these would be relics of a primordial magnetization, dim but pervasive. Studying this invisible architecture requires clever eyes. Light that passes through magnetized plasma can have its polarization rotated, a phenomenon called Faraday rotation, offering a compass to the field's strength and direction along the line of sight. Dust grains in the ISM align with fields and polarized starlight, tracing the local geometry like iron filings around a bar magnet. Electrons spiraling along field lines emit synchrotron radiation at radio wavelengths, mapping where the fields are strongest and most tangled. With arrays like LOFAR, the VLA, ALMA, and the rising promise of the Square Kilometer Array, astronomers are assembling magnetic atlases of clouds, galaxies, and clusters, while numerical magnetohydrodynamic simulations test how those fields evolve, break, and reconnect. Reconnection, where field lines snap and rejoin in new configurations, turns magnetic energy into heat and motion with sudden efficiency. On the sun, it powers flares. In disks, it can energize jets. In clusters, it may help dissipate turbulence. In the extreme hearts of dead stars, magnetars' fields roar to unimaginable strengths, and their fractures can jolt space with gamma-ray flares, a reminder that magnetism can be as violent as it is gentle. Thread by thread, magnetic fields moderate, organize, and regulate. They slow some collapses and hasten others, carve channels for winds, braid jets, and quiet the riot of turbulence into something galaxies can live with. They give cosmic rays a path and the ISM a backbone. They help set the tempo at which stars light, planets form, and feedback breathes in and out of galactic lungs. Though our eyes cannot see them, their touch is everywhere in the calm of Earth's auroras, in the discipline of spiral arms, in the vast radio glows that halo clusters, and perhaps in the faintest filaments between galaxies, humming with an ancient, patient current. If you listen softly to the night sky past the glitter of stars, beneath the drift of dust you might sense the fields as a kind of low music. Not a melody, exactly, but a steady undertone, keeping time while gravity writes the dance. In that undertone lives a subtle promise that the universe is not only pulled together by mass, but also guided by invisible lines of force, quiet hands that shape the dark into forms that shine. Between the stars, where the night seems quietest, the galaxy breathes. That breath is the interstellar medium, the ISM, a faint, living tide of gas, dust, and cosmic rays that threads every spiral arm and halo. It is only about 1% dust by mass, the rest mostly hydrogen, with a whisper of helium and traces of carbon, nitrogen, oxygen, and heavier elements. Yet this thin material is the cradle and the cemetery of stars, the pantry of planets, the page on which a galaxy writes and rewrites itself. The ISM does not have a single temperature or a single mood. It is a patchwork quilt of phases, stitched by shock waves and starlight, gravity and magnetism. In its coldest corners, molecular clouds shiver at tens of Kelvin, their interiors hidden by dust that blocks harsh radiation. Here, hydrogen binds into H2, carbon joins oxygen to make CO, and ices coat grains with water, methanol, and more delicate organics, simple beginnings for complicated futures. Elsewhere, the gas is warm and mostly neutral, drifting at thousands of Kelvin in wide, translucent seas. Threaded through and above the disk lies a diffuse, warm, ionized medium, kept gently aglow by the scattered ultraviolet of massive stars. And where supernovae have recently flared, the gas is a million Kelvin wind, a hot, ionized medium filling superbubbles and chimneys that vent energy from the starry plains below into the galaxy's higher air. The ISM is a conversation between light and matter. Around newborn O and B-type stars, clouds become H2 regions, spheres where ultraviolet photons strip electrons from hydrogen. Their edges are delicate borders, photon-dominated regions, where chemistry rearranges itself under a patient rain of starlight. Farther in, where darkness is nearly complete, the chemistry grows more elaborate. Dust grains act as meeting places and shelters. Atoms cling to their surfaces, react, and depart as molecules that could not easily assemble in the open gas. Tiny carbonaceous particles and PAHs, polycyclic aromatic hydrocarbons, soak up ultraviolet light and re-emit it as a soft infrared glow, a low ember that reveals the dust's invisible architecture. Dust does more than hide and shine. It reddens and extinguishes starlight, changing what we see and what we might mistake. It seeds planets by sticking into pebbles, pebbles into boulders, and boulders into worlds. Long after the star that warmed the original cloud has settled onto the main sequence, it also cools gas by radiating away heat, allowing gravity to gain the upper hand where it otherwise would not, and dust polarizes starlight. Grains align with magnetic fields like compass needles, imprinting a subtle signature that lets astronomers trace the unseen threads that guide the gas. Those magnetic fields give the medium structure and patience. Coupled to partially ionized gas, they resist collapse in some directions and ease flows in others, stretching clouds into filaments and channels. Along them, cosmic rays, swift charged particles born in supernova shocks, stream through the galaxy, adding pressure, ionizing dark interiors, and helping to drive winds from galactic disks. Together with turbulence stirred by stellar feedback, these forces set the rhythm of star formation. Not a blaze, but a heartbeat efficient enough to keep the lights on, inefficient enough to let the pantry last. Star birth begins with a nudge. A passing spiral density wave compresses a cloud. A supernova shell brushes its flank. An expanding Nuc-2 region presses on a dark ridge. Pockets tip past Gene's instability and begin to fall inward. As they collapse, they fragment, conserving angular momentum and flattening into rotating envelopes and disks. The densest knots become protostars, cocooned in dusty blankets. Around them, protostellar disks spin like small, warm ponds, reflecting the light of a hidden ember. Magnetic torques and the magnetorotational instability help the inner gas shed angular momentum and drift onto the growing star, while twin jets lance outward along the field lines, clearing cavities. The surrounding cloud, jostled by these jets and by outflows and radiation, is both eroded and provoked. One star's birth often encourages another's, but never in a straight line. Not all cold gas makes stars. The star formation efficiency of a giant molecular cloud is small. Most of its mass will be returned to the ISM. Massive newborns live fast, flood their neighborhoods with ionizing light and winds, and then end in supernovae that carve hot, tenuous bubbles. Those bubbles merge into superbubbles that punch through the disk, venting into the halo as fountains. The ejected gas cools, rains back in curtains, and blends again with the warm and cold phases below. In this way, the ISM practices a long, patient recycling. Matter moves from cloud to star to cloud again, gathering metals forged in stellar cores, carbon, oxygen, silicon, iron that enrich the next generation of stars and the planets that may form around them. The ISM also connects the galaxy to its wider environment. At the edge where disk meets halo, outflows carry metals and energy upward. Inflows drift down along the galaxy's gravitational wells, sometimes funneled by filaments of the cosmic web. The circumgalactic medium is the ISM's wide frontier, thin, ionized, and sprawling, where the galaxy trades heat and mass with the larger sky. Spectra of distant quasars, scratched by the fine lines of intervening gas, reveal these exchanges, a ledger written in absorption, tallying what has been given and received. Within the ISM's quilt are places so vivid they need names. The Orion Nebula is one, a bright blister on the side of a giant cloud, where a young cluster's light peels back the dark and lets us watch a nursery at work. There, pillars and proplids, proto-planetary disks, silhouette against ionized glow, and every wavelength from radio to X-ray adds a stitch to the story. Reflection nebulae shimmer with the blue of scattered starlight. Emission nebulae breathe with the red of alpha. Dark nebulae appear as inks spilled across the Milky Way, not empty at all, but too full of dust for starlight to pass. Supernova remnants the veil, the crab ripple with filaments, where shocks compress and heat gas, accelerating electrons to radiate in curling lines we can trace in radio maps. Energy moves through the ISM in many dialects. In hot plasma, electrons and ions collide and free radiation carries heat away. In warm and cold phases, fine structure lines from carbon, oxygen, and nitrogen, and rotational lines from molecules like CO act as coolants that let gas settle and gather. Ultraviolet radiation breaks molecules and shapes chemistry. Cosmic rays knit them back together in deeper shadows. The balance changes from place to place, hour to hour, star to star, but over millions of years, the averages hold well enough for a spiral arm to keep breathing. To read this hidden world, astronomers use whichever light the medium will give. 21-centimeter radio waves trace neutral hydrogen through the disk and into the halo. Millimeter emission from CO and rarer tracers maps the skeleton of molecular clouds, revealing filaments, hubs, and the seeds of clusters. Infrared missions catch the glow of dust and PAHs, outlining where young stars warm their cradles. Optical and ultraviolet spectra write the chemistry and the motions into narrow lines. X-rays outline the hot interiors of superbubbles. Polarization maps from starlight and dust emission trace magnetic geometry. Synchrotron radio maps sketch where electrons spiral along the fields, and where even emission is too faint, absorption steps in. The fingerprints of the ISM etched into the light of a background star or quasar, a shadow that says, "I am here," because the ISM is dynamic. It also remembers every heavy element it holds once lit the heart of a star. Every shockwave is the echo of a life ending or a cluster stirring. The distribution of phases, how much is cold enough for clouds, how much warm enough to drift, how much hot enough to climb, records a galaxy's recent weather, its star formation rate, its feedback, its inflow and outflow. Spiral arms compress gas and then pass on. Bars funnel material toward galactic centers, where it may feed rings of new stars or the hunger of a central black hole. In dwarfs, a single starburst can sweep gas away. In giants, many bursts overlap, stirring the disk but never emptying it. If you could hold a pinch of the ISM in your hand, it would seem like nothing at all. A cubic centimeter might host a single atom, or in the densest cores, 1,000, but spread across hundreds of thousands of light years. This nearly nothing becomes everything. The reservoir for future suns, the laboratory where chemistry learns to be complex, the soft scaffolding that keeps a galaxy responsive to its own heartbeat. The stars owe their birth to it. Planets owe their minerals to it. We owe our breath to the oxygen it learned to carry and return. So the ISM is not the space between stories. It is the story between spaces, the lullaby underneath stellar noise, the slow current that gathers, releases, and gathers again. Drift there in your mind for a moment. Cold, dark filament, warm, diffuse sea, hot, bright shell, and back again. Hear the faint tick of dust cooling, the low murmur of ions, the distant crackle of a remnant fading. This is the galaxy's long inhale and exhale, the quiet work that makes nights full of stars. And now, as the echoes of the cosmos begin to fade, let yourself drift with them softly, slowly. The stars that once shimmered so brightly above you dim to a gentle glow, like embers breathing their final warmth into the night. The great rivers of starlight stretch across an endless sky, flowing quietly toward dreams you cannot name. You breathe in, and the universe breathes with you, a rhythm older than time, calmer than silence. Every thought loosens, every sound melts into stillness. The questions of galaxies, of light and distance, of beginnings and ends, all dissolve into a single, peaceful hum. Let that hum cradle you now. Feel your body grow lighter, your mind quieter, your breath blending with the dark. Somewhere between one heartbeat and the next, you are no longer watching the stars, you are part of them, floating through their silver glow. The night deepens, the light fades, and you drift gently into the quiet arms of sleep.